Welcome to Cosmic Crossroads, the channel where the mysteries of the universe unfold before your very eyes. Today, we embark on an unprecedented journey through our solar system, an odyssey spanning over 3 hours, dedicated to exploring every corner of our celestial neighborhood. From the scorching surface of Mercury to the icy realms of Pluto, we dive deep into the heart of each planet, uncovering their secrets one by one. Our voyage begins with the innermost planet, Mercury, exploring its cratered landscapes and enduring the extreme temperatures that define its existence. We then glide towards Venus, shrouded in thick clouds, revealing the inferno that lies beneath its atmospheric veil. The Earth, our pale blue dot, is examined not just as our home, but as a dynamic entity, with a life story that intertwines with every living creature on its surface. Mars, the red warrior of the sky, offers us tales of water, ice, and the endless search for life beyond our planet. As we venture beyond the asteroid belt, we encounter the gas giants, Jupiter, with its great red spot and multitude of moons, and Saturn, encircled by its magnificent rings. Uranus and Neptune, the ice giants, mystify us with their tilted orbits and fierce winds. Our journey doesn't end at Neptune. We travel further, to the dwarf planet Pluto, once the 9th planet of our solar system. Here, at the edge of our cosmic doorstep, we delve into the debate of what defines a planet and celebrate the diversity and complexity of the worlds that share our sun. Mercury, the innermost planet of our solar system, presents a world of extremes and mysteries. Closer to the Sun than any other planet, it races through space at a breakneck speed, completing an orbit in just 88 Earth days. Despite its proximity to the Sun, Mercury is not the hottest planet, a title held by Venus, but it experiences the most significant temperature fluctuations in the solar system. As we journey through space to explore Mercury, we delve into its unique characteristics, from its craterid surface that tells stories of the solar system's early days, to the peculiarities of its rotation and orbit that create a world of both eternal sunlight and eternal darkness. Join us as we uncover the secrets of Mercury, a small yet fascinating world that offers insight into the formation of our solar system and the conditions of celestial bodies close to their stars. Mercury's physical characteristics are as fascinating as they are extreme. With a diameter of about 4,880 kilometers, Mercury is the smallest planet in our solar system, only slightly larger than Earth's moon. Despite its diminutive size, Mercury packs a significant punch with a density nearly equal to that of Earth, indicating it possesses a large, iron-rich core. This core makes up about 60% of Mercury's total mass, a proportion unmatched by any other planet in our solar system, suggesting a violent past where it might have lost its outer layers to solar winds or a catastrophic impact. The surface of Mercury is a testament to its ancient history, heavily cratered and similar in appearance to the Moon, telling tales of a tumultuous early solar system where it was bombarded by comets and asteroids. Among these craters, the Caloris Basin stands out as one of the largest, a vast impact crater over 1,550 kilometers in diameter, showcasing the violent processes that shaped Mercury's youth. Mercury's thin atmosphere, or exosphere, is composed of atoms blasted off its surface by solar radiation, including oxygen, sodium, hydrogen, helium, and potassium. This thin veil cannot retain heat, leading to the planet's extreme temperature variations. Temperatures on Mercury's surface can soar to 430 degrees C, 800 degrees C during the day, hot enough to melt lead, and plummet to 180 degrees C to 90 degrees C at night, due to the absence of a significant atmosphere to trap the sun's heat. Another intriguing physical characteristic of Mercury is its peculiar rotation. It rotates on its axis very slowly, taking about 59 Earth days to complete one rotation, but it orbits the Sun in just 88 days. This results in a unique phenomenon where at certain points on Mercury's surface, an observer could see the Sun rise, then briefly set, only to rise again, all within the same Mercurian day. This is a consequence of Mercury's 3-2 spin-orbit resonance, where the planet completes 3 rotations for every 2 orbits around the Sun. Exploring Mercury's physical characteristics reveals a planet of contrasts and extremes, from its dense metallic core to its sun-scorched surface and the stark temperature contrasts that define its days and nights. Mercury challenges our understanding of planetary formation and evolution, offering a window into the processes that have shaped our solar system. Mercury's orbit and rotation present one of the most unique dynamical systems in the solar system, revealing a celestial dance that defies the more straightforward movements of its planetary neighbors. Orbiting the Sun at an average distance of approximately 58 million kilometers, about 36 million miles, Mercury is the closest planet to our star. Its orbit is highly eccentric, the most elliptical of all the planets, ranging from 46 million kilometers, about 29 million miles, at its closest approach, perihelion, to 70 million kilometers, about 43 million miles, at its furthest, aphelion. This elliptical orbit results in significant variations in Mercury's speed as it travels around the Sun, moving faster at perihelion and slower at aphelion, a vivid demonstration of Kepler's laws of planetary motion. The planet's rotation is equally unusual. Mercury spins slowly on its axis, taking about 58.6 Earth days to complete one rotation. This slow spin, combined with its 88 Earth day orbit around the Sun, leads to a fascinating outcome. Mercury has a 3.2 spin-orbit resonance. This means that for every 2 orbits it completes around the Sun, it rotates 3 times on its axis. As a result, one day on Mercury, from sunrise to sunrise, is 176 Earth days long, twice as long as its year. This resonance is thought to be the result of tidal interactions with the Sun, gradually altering Mercury's rotation over millions of years to reach this unique state. Furthermore, the angle of Mercury's axis of rotation is nearly perpendicular to the plane of its orbit, with an axial tilt of just about 0.034 degrees. This is the smallest tilt of any planet in the solar system, which means Mercury does not experience seasons in the same way that Earth or Mars does. The Sun's position in the sky on Mercury does not vary significantly with the planet's position in its orbit, leading to relatively stable temperatures in any given location, albeit with extreme differences between day and night due to the lack of a substantial atmosphere. Mercury's orbit and rotation not only influence its day and night cycle, but also have profound implications for its surface conditions and the environment experienced by spacecraft visiting the planet. The extreme eccentricity of its orbit and its unique spin-orbit resonance make Mercury a fascinating subject of study for understanding the dynamics of celestial bodies and their interactions with their parent stars. The exploration and observation of Mercury have provided invaluable insights into the innermost planet of our solar system, revealing its complex environment and history. Due to its proximity to the Sun and the resulting technical challenges, missions to Mercury are less common than to other planets. However, the endeavors undertaken have significantly advanced our understanding of this enigmatic world. The first spacecraft to visit Mercury was Mariner 10, launched by NASA in 1973. Utilizing a gravitational assist from Venus, Mariner 10 made 3 flybys of Mercury in 1974 and 1975, mapping about 45% of its surface. This mission unveiled the planet's heavily cratered terrain, its lack of a substantial atmosphere, and its magnetic field, a surprising discovery given Mercury's small size. Decades later, NASA's Messenger spacecraft, launched in 2004, became the first to orbit Mercury in 2011. Over 4 years, Messenger revolutionized our understanding of Mercury, confirming its unusually high metal content and discovering water ice in permanently shadowed craters near its poles. The mission provided detailed maps of Mercury's surface, explored its geology, and investigated its thin exosphere and magnetosphere. Messenger's observations confirmed that volcanic activity and tectonic movements have shaped Mercury's surface in the past, suggesting a more dynamic history than previously thought. The European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA, have joined the effort to explore Mercury with the Bepi-Colombo mission, launched in 2018. This ambitious mission consists of two spacecraft, the Mercury Planetary Orbiter, MPO by ESA, and the Mercury Magnetospheric Orbiter, MMO by JAXA. Bepi-Colombo aims to build on MESSENGER's discoveries, investigating Mercury's magnetic field, magnetosphere, and interior structure in greater detail. Its journey includes a series of complex flybys of Earth, Venus, and Mercury itself, utilizing gravity assists to navigate closer to the planet, with the goal of entering Mercury's orbit in 2025. Ground-based observations have also contributed to our knowledge of Mercury. Telescopes equipped with radar have been used to detect ice in the planet's shadowed craters, while optical and infrared telescopes have studied its surface composition and monitored the exosphere. These observations complement space missions by providing a broader context for understanding Mercury's environment and its place in the solar system. The exploration and observation of Mercury challenge the boundaries of our technology and knowledge. Each mission and observation brings us closer to unraveling the mysteries of the smallest planet, offering insights not only into its nature, but also into the processes that govern the solar system's innermost regions. The significance of Mercury in our understanding of the solar system cannot be overstated. As the closest planet to the Sun, Mercury provides a unique laboratory for studying planetary formation, evolution, and the dynamics of solar systems. Its extreme conditions, peculiar orbit, and geological features offer clues to the processes that shaped the early solar system and influenced planetary bodies. Mercury's large iron core, relative to its size, offers insight into the differentiation and formation of planetary interiors. Understanding. Mercury's core is crucial for models of planetary formation and evolution, providing comparisons to Earth and other terrestrial planets. The study of Mercury's magnetic field generated by its core also sheds light on the dynamo processes that create magnetic fields around other planets. The surface of Mercury, with its extensive cratering, acts as a historical record, preserving evidence of the solar system's early years. Studying these craters and the geological processes that have modified Mercury's surface over billions of years helps scientists understand the frequency and impact of celestial collisions in the inner solar system. Mercury's proximity to the Sun and its lack of a significant atmosphere result in the most extreme temperature variations in the solar system, alongside intense solar radiation. Studying how these conditions affect Mercury's surface and exosphere provides valuable data on the survivability of materials and potential life in similar extreme environments elsewhere in the universe. Mercury's unique 3-2 spin-orbit resonance and its highly eccentric orbit offer a natural experiment for understanding celestial mechanics, particularly the effects of tidal forces and orbital resonances. These insights have broader implications for the study of exoplanets and their orbits around distant stars. Mercury plays a key role in the study of general relativity. Its orbit exhibits precession that cannot be fully explained by Newtonian mechanics, but is accurately predicted by Einstein's theory of general relativity. Observations of Mercury, therefore, provide a crucial test for our understanding of gravitational phenomena. While Mercury itself is inhospitable to life as we know it, studying its ability to harbor water ice in permanently shadowed craters at its poles expands our understanding of where water, and potentially life, could exist in unexpected conditions. This challenges and informs the search for life in other parts of the galaxy. In summary, Mercury's significance extends far beyond its status as the smallest planet in our solar system. Its study impacts a broad range of scientific fields, from planetary science and astrophysics to the study of celestial dynamics and the fundamental laws of physics. Through missions like Mariner 10, Messenger, and Bepi-Colombo, along with ground-based observations, Mercury continues to be a key target for unlocking the mysteries of our solar system and beyond. In conclusion, Mercury, with its blistering days, frigid nights, and swift journey around the Sun, stands as a beacon of discovery in the celestial wilderness of our solar system. This enigmatic planet, though small in stature, looms large in its contributions to our understanding of planetary science, celestial mechanics, and the early history of our solar neighborhood. From the groundbreaking revelations of Mariner 10 to the comprehensive insights of Messenger and the ongoing explorations by Bepi Colombo, Mercury continues to unveil its secrets, challenging our assumptions and expanding our knowledge. Mercury serves not only as a testament to the dynamic processes that govern our solar system, but also as a reminder of the vast unknowns that await discovery. Each mission to this rugged little planet peels back another layer of mystery, revealing the intricate dance of forces that shape our universe. Mercury's significance extends beyond its orbit, offering a window into the fundamental principles of astrophysics and providing a critical comparison point for understanding other terrestrial planets and exoplanetary systems. Mercury remains a key destination for future exploration, promising to unlock further secrets about the formation of planets, the behavior of celestial bodies in extreme conditions, and the potential for life in the universe's far-flung corners. The ongoing study of Mercury underscores humanity's unending quest for knowledge, pushing the boundaries of what we know and expanding the horizons of our cosmic understanding. In the grand tapestry of the solar system, Mercury is a vital thread, weaving together stories of creation, evolution, and the enduring quest to understand our place in the universe. Venus, our solar system's second planet from the Sun. Often heralded as Earth's sister planet, Venus shares many characteristics with our home, such as size, mass, and a rocky composition, making it a fascinating subject of study in our quest to understand the universe. Yet for all its similarities, Venus is a world apart, veiled in a thick, toxic atmosphere that conceals its surface from direct view. This shroud of carbon dioxide and clouds of sulfuric acid creates a runaway greenhouse effect, making Venus the hottest planet in our solar system, a stark contrast to the life-supporting conditions on Earth. As we embark on this visual exploration, we'll delve into the mysteries of Venus's scorching climate, its retrograde rotation, and volcanic landscape, shedding light on why this planet, named after the Roman goddess of love and beauty, is anything but gentle and serene. Join us as we explore Venus, a planet that teaches us about the extremes of planetary environments, and through understanding its past, helps us to envision the future of our own world and others that lie beyond the stars. Venus, often dubbed Earth's enigmatic sister, harbors an atmosphere that is as intriguing as it is inhospitable. Imagine a thick blanket composed primarily of carbon dioxide, enveloping the planet in a tight embrace. This dense atmospheric layer is not alone. It is accompanied by clouds filled with sulfuric acid, painting a picture of a world where the term extreme is an understatement. The atmosphere of Venus is a testament to the runaway greenhouse effect gone to the extreme. Here, the concept of a greenhouse effect, familiar to us on Earth, is amplified to levels that challenge our understanding. The thick carbon dioxide traps heat with ruthless efficiency, making Venus the hottest planet in our solar system. This is a world where temperatures soar to around 470 degrees Celsius, 878 degrees Celsius, a searing heat capable of melting lead and crushing any aspirations of human visitation with its oppressive force. This intense heat is not merely a surface phenomenon, but permeates throughout the planet's atmosphere, creating conditions that are markedly different from the chilly void of space just beyond. The pressure at Venus's surface is a crushing 92 times that of Earth, akin to being nearly a kilometer underwater in Earth's oceans. This pressure, combined with the heat, creates a surface environment that is nothing short of hellish. The clouds of Venus play a significant role in its atmospheric dynamics. These are not the water vapor clouds we are familiar with on Earth, but are instead composed of sulfuric acid. They reflect a significant amount of sunlight, giving Venus its brilliant shine and making it one of the brightest objects in our night sky. However, this reflective quality also contributes to the greenhouse effect, trapping heat and ensuring the surface remains an inferno. Despite its harsh conditions, Venus's atmosphere offers a unique laboratory for studying extreme climate systems. Scientists are particularly interested in understanding the dynamics of Venus's super-rotating atmosphere, where winds circulate the planet much faster than the planet itself rotates. This phenomenon, coupled with the thick cloud cover, makes direct observation of the surface challenging but not impossible. Recent missions and telescopic observations have begun to peel back the layers of Venus's veiled atmosphere, offering glimpses into its complex weather patterns, including thick cloud cover and mysterious dark streaks known as unknown absorbers that capture a significant amount of solar radiation. These features, along with the lightning detected in the Venusian atmosphere, hint at a dynamic and ever-changing world, beckoning scientists to uncover its secrets. The study of Venus's atmosphere is not just an academic pursuit. It offers a cautionary tale of the greenhouse effect gone awry and provides critical insights into our own climate challenges on Earth. By understanding Venus, we may find keys to safeguarding our own planet's future, ensuring that Earth's atmosphere remains hospitable and vibrant, a stark contrast to the broiling veil that shrouds our sister planet. As we continue to peer through the acidic clouds and probe the depths of this alien atmosphere, Venus stands as a reminder of the delicate balance that sustains life on Earth and the profound mysteries that our solar system holds. Venus, often shrouded in mystery due to its dense atmosphere, reveals a surface that tells a story of volcanic activity, extreme pressures, and a geologic history that continues to fascinate scientists. Beneath the thick clouds, Venus is a world of extremes, its landscape shaped by forces both familiar and alien to those we know on Earth. The surface of Venus is dominated by vast plains, sprawling mountain ranges, and tens of thousands of volcanoes, more than any other planet in our solar system. Among these volcanoes are shield volcanoes, similar to those found in Hawaii, suggesting that Venus has been geologically active for millions of years. However, Venus lacks the tectonic plate activity seen on Earth, leading to a different kind of volcanic activity and mountain formation. One of the most striking features on Venus is Maxwell Montes, the highest mountain range on the planet, towering about 7 miles above the Venusian surface. This mountain range, along with the numerous highland areas, hints at a complex geologic history involving both volcanic activity and the planet's own unique form of tectonics. The plains of Venus are covered with volcanic flows, indicating that lava once flowed across the surface, reshaping the landscape. Radar imaging has revealed that these plains are relatively young, geologically speaking, suggesting that Venus is still geologically active. Despite its rocky surface, Venus shows no evidence of liquid water today. However, there are signs that water may have existed in the past. Certain geological features hint at erosion and other water-related processes, leading scientists to speculate that Venus might have once had oceans, possibly making it more Earth-like in its early history. Craters dot the Venusian landscape, but not as many as one might expect. This scarcity of craters indicates that the surface of Venus is relatively young, having been resurfaced by volcanic activity within the last few 100 million years. The craters that do exist are well preserved, with some surrounded by complex radar-bright halos, suggesting material ejected during impact. The geology of Venus provides a glimpse into a world both similar to and vastly different from Earth. Its volcanic activity, lack of water, and unique surface features offer valuable insights into planetary formation, evolution, and the conditions that might exist on other rocky planets in our galaxy and beyond. As we continue to explore Venus, its surface and geology will undoubtedly continue to reveal secrets about our sister planet's past, present, and future. Venus, our celestial neighbor, presents one of the most fascinating orbital and rotational dynamics in our solar system. As we delve into its journey around the Sun, we uncover characteristics that distinguish Venus from other planets, shedding light on its unique place in the cosmic ballet. Firstly, Venus orbits the Sun at an average distance of about 108 million kilometers, or 67 million miles, completing a full circle every 224.7 Earth days. This relatively short orbital period places Venus closer to the Sun than Earth, nestled within the inner solar system's warm embrace. The proximity to the Sun, however, is not solely responsible for Venus's notorious heat. Instead, it's the planet's dense atmosphere that plays a pivotal role in trapping solar radiation, leading to surface temperatures that soar to a blistering 465 degrees Celsius, 869 degrees Fahrenheit. But it's not just Venus's orbit that intrigues scientists and space enthusiasts alike. The planet's rotation on its axis is equally captivating, primarily because it defies the norm observed in most other planets. Venus rotates on its axis in a direction opposite to its orbit around the Sun, a phenomenon known as retrograde rotation. This means that on Venus, the Sun would appear to rise in the west and set in the east, opposite to what we experience on Earth. Adding to its list of peculiarities, Venus's rotation is remarkably slow. It takes about 243 Earth days for Venus to complete one rotation, making a single day on Venus longer than a Venusian year. This slow rotation contributes to extreme variations in temperature from day to night, further complicating the planet's already hostile environment. Moreover, the tilt of Venus's axis is almost negligible, less than 3 degrees, compared to Earth's 23.5 degrees. This minimal tilt means that Venus does not experience seasons as Earth does. The combination of its slow retrograde rotation and slight axial tilt has puzzled scientists for years, leading to numerous theories about the planet's formation and evolutionary history. Understanding Venus's orbit and rotation is crucial not only for comprehending the planet's climate and geological processes, but also for planning future missions. As we continue to explore Venus, these fundamental aspects of its nature will guide our efforts to unlock the mysteries of this enigmatic world, offering insights into the formation and dynamics of planets both within our solar system and beyond. In recent years, Venus has surprised scientists with revelations that challenge our understanding and ignite our curiosity. One of the most tantalizing discoveries came when astronomers detected traces of phosphine gas in Venus's atmosphere, a chemical typically produced by biological processes on Earth. This finding sparked a global conversation about the possibility of microbial life in the cloud decks of Venus, where temperatures and pressures are less extreme. While subsequent studies have both challenged and supported these findings, the debate underscores our limited knowledge of Venus and the potential it holds for breakthroughs in astrobiology. Geologically, Venus continues to reveal its secrets. High-resolution mapping and radar imaging from past missions have suggested that Venus is not a dormant world, but one possibly teeming with volcanic activity and tectonic movements. These observations hint at a dynamic planet that may be reshaping its surface more frequently than previously thought, offering insights into planetary geology and the life cycle of terrestrial planets. Looking to the future, the international scientific community is preparing for an unprecedented wave of exploration aimed at Venus. NASA's Veritas, Venus Emissivity, Radio Science, INSAR, Topography and Spectroscopy. Mission and ESA's Envision mission are set to launch in the next decade, equipped with advanced instruments designed to map the planet's surface in greater detail than ever before, analyze its geological composition, and investigate its atmosphere. These missions aim to answer key questions about Venus's past and present, including whether it once harbored oceans and how it underwent such a dramatic transformation into the inhospitable world we see today. Additionally, India's space agency, ISRO, plans to launch the Shukrayaan-1 mission to study Venus's atmosphere in detail, focusing on understanding its chemical composition, dynamics, and interaction with solar radiation and the solar wind. These missions collectively represent a renaissance in Venus exploration, driven by a growing recognition of its importance in understanding not only the diversity of planets in our own solar system, but also the characteristics of potentially habitable worlds orbiting other stars. As we stand on the brink of these exciting endeavors, Venus reminds us of the boundless potential for discovery that our neighboring planets hold. The coming years promise to reshape our understanding of Venus, offering new perspectives on the mysteries of our solar system and beyond, and possibly on the origins of life itself. The journey to unlock the secrets of Venus is just beginning, and what we find could alter our place in the cosmos forever. As we draw our journey to Venus to a close, it's clear that this enigmatic world is more than just a mere point of light in our night sky. Venus, with its extreme conditions and mysterious landscape, serves as a stark reminder of the dynamic and diverse nature of the planets in our solar system. It challenges our understanding of planetary science, climate change, and the potential for life in the universe. The study of Venus is not just an academic pursuit, it holds the key to unraveling the past, present, and future of our own planet, Earth. The similarities and differences between these two worlds provide critical insights into how terrestrial planets evolve and the effects of greenhouse gases on atmospheric conditions. By understanding Venus, we may find answers to some of the most pressing questions about our own planet's climate and environmental future. Moreover, the ongoing interest and future missions to Venus underscore our never-ending quest for knowledge and the human spirit of exploration. Each mission brings us one step closer to answering age-old questions. Are we alone in the universe? How unique is Earth in its ability to support life? The potential for discovering signs of past or present life on Venus, however remote, fuels our imagination and drives forward our scientific endeavors. As we look to the future, let's continue to support and anticipate the international efforts to explore Venus further. The mysteries that Venus holds are not just scientific curiosities, they are beacons that draw us together in our shared quest for knowledge. The challenges of exploring Venus push the boundaries of technology, international cooperation, and our understanding of life itself. So let's keep our eyes turned skyward, filled with wonder and curiosity. The story of Venus, much like the rest of the universe, is still being written. And who knows what incredible discoveries await us as we delve deeper into the secrets of our sister planet. Thank you for joining me on this exploration of Venus. May your curiosity about the universe never fade, and may the pursuit of knowledge always light your way. Until next time, keep exploring and never stop wondering about the wonders of our solar system and beyond. Welcome to a captivating journey to Earth, our oasis in the vast emptiness of space. Known as the Blue Planet due to its abundant water and lush appearance from afar, Earth is the third planet from the Sun and the only known place in the universe where life exists. With a perfect blend of atmospheric conditions, distance from the Sun, and protective magnetic fields, Earth is a unique haven for a diverse array of life forms. As we embark on this exploration, we'll dive into Earth's dynamic atmosphere, its ever-changing climate, and the intricate systems that sustain life. From the deepest oceans to the highest mountains, Earth's landscapes are as diverse as the creatures that inhabit them. This journey will take us through the planet's geological history, uncovering the forces that have shaped its continents and oceans over billions of years. Join us as we celebrate Earth's natural wonders, investigate its environmental challenges, and discover the interconnectedness of all living things. Whether you're a passionate environmentalist or simply curious about the planet we call home, this exploration of Earth promises to inspire and educate, highlighting the importance of stewardship and conservation for future generations. Let's embark on this voyage of discovery, celebrating the beauty and complexity of Earth, our home in the cosmos. Through understanding our planet's past, present, and potential futures, we can appreciate the fragility and resilience of the home that sustains us and all life as we know it. Our home planet, Earth, is enveloped in a life-sustaining atmosphere, a thin veil of gases that stands as the boundary between the surface of our world and the vast expanse of space. Unlike the hostile environs of our neighbor Venus, Earth's atmosphere is a delicate balance of components that have fostered and sustained life for billions of years. At the heart of Earth's atmosphere is a mixture primarily composed of nitrogen, about 78%, and oxygen, about 21%, with traces of argon, carbon dioxide, and other gases. This composition is crucial for life as we know it. Oxygen supports the breath of countless organisms, while nitrogen plays a vital role in the structure of DNA and the air we breathe. One of the most remarkable features of Earth's atmosphere is its ability to regulate temperature through the greenhouse effect, a natural process that traps heat from the sun. Water vapor, carbon dioxide, methane, and other greenhouse gases absorb and emit infrared radiation, keeping the planet warm enough to support life. This process is finely balanced. Too little greenhouse effect, and the Earth would freeze. Too much, and it would become a sweltering hothouse as seen on Venus. Earth's atmosphere is not just a static shield, but a dynamic system that influences and is influenced by the planet's weather and climate. The atmosphere is divided into layers, each with its characteristics and processes. The troposphere, where weather happens, the stratosphere, home to the ozone layer that protects life from harmful ultraviolet radiation, and higher layers like the mesosphere, thermosphere, and exosphere, each play a role in Earth's complex atmospheric ballet. Clouds formed from water vapor are a defining feature of Earth's atmosphere. They play a critical role in the global water cycle and climate system, reflecting sunlight back into space and trapping heat within the atmosphere. This interplay of heating and cooling is a delicate balance that regulates Earth's climate. Human activity has begun to tip this balance, with the burning of fossil fuels and deforestation increasing the concentration of greenhouse gases in the atmosphere. This enhanced greenhouse effect is leading to global warming and climate change, posing a significant challenge for life on Earth. The parallels to Venus's extreme greenhouse effect are a stark reminder of the importance of maintaining the delicate balance that makes our planet habitable. The Earth's atmosphere also serves as a protective barrier, shielding life from meteoroids and the sun's harmful radiation. The magnetosphere, an extension of the atmosphere in interaction with Earth's magnetic field, deflects solar wind and cosmic rays, further protecting the biosphere. Our understanding of Earth's atmosphere has grown through observation, study, and exploration. It is a dynamic system that requires careful stewardship to maintain the balance necessary for life. As we look to the stars and explore planets like Venus, we are reminded of the uniqueness of Earth's atmosphere and the critical importance of preserving it for future generations. The atmosphere of Earth is more than just air. It is the breath of our planet, a complex system that sustains life, influences weather and climate, and protects us from the harshness of space. As we continue to explore and understand this delicate envelope, we are learning not just how to safeguard our own world, but also gaining insights into the atmospheres of distant planets, broadening our knowledge of the universe and our place within it. Earth, our home planet, presents a dynamic and diverse geological tapestry that tells the story of over 4.5 billion years of history. Unlike any other planet in our solar system, Earth's surface is a living, breathing entity, constantly reshaped by the forces of nature. It's a planet where life has flourished, influencing and being influenced by the geological processes at work. The surface of Earth is a mosaic of contrasting landscapes, ranging from the frozen expanses of Antarctica to the scorching deserts of Africa. About 71% of Earth's surface is covered by water, primarily in the form of oceans, seas, lakes, and rivers. This abundance of water is a defining feature of our planet, crucial for the existence of life as we know it. The remaining 29% of Earth's surface is land, consisting of continents and islands with a wide variety of geological features. These include towering mountain ranges like the Himalayas, formed by the collision of tectonic plates, vast plains and plateaus that serve as the breadbaskets of the world, and deep valleys and canyons carved out by rivers and glaciers over millennia. At the heart of Earth's geology is the theory of plate tectonics, which explains the movement of the Earth's lithosphere, divided into several large and small plates. These tectonic plates float on the semi-fluid asthenosphere beneath them, and their interactions are responsible for much of the geological activity we observe, including earthquakes, volcanic eruptions, and the formation of mountain ranges. Volcanoes are a dramatic manifestation of Earth's geological activity, with the Ring of Fire in the Pacific Ocean being one of the most active regions. Volcanic eruptions, while potentially destructive, also play a vital role in shaping Earth's surface and atmosphere, contributing to the planet's ability to support life. Erosion and sedimentation are constant forces shaping Earth's surface, driven by water, wind, and ice. These processes break down rocks and minerals, transporting them to new locations where they form sedimentary layers. Over time, these sediments can be compressed and cemented into sedimentary rock, or subjected to heat and pressure to form metamorphic rock. The rock cycle is a fundamental concept in geology, illustrating the transformation of rocks through different forms over geological timescales. Water is a powerful agent of change on Earth's surface, capable of carving canyons, shaping coastlines, and eroding mountains. The presence of liquid water, unique among the planets in our solar system, has not only sculpted Earth's surface, but also created the conditions necessary for life to evolve and thrive. The surface and geology of Earth are a testament to the dynamic processes that have shaped our planet over billions of years. From the highest mountains to the deepest ocean trenches, every feature tells a part of the story of Earth's geological past and provides clues to understanding the planet's future. As we continue to explore and study Earth's geology, we gain not only insights into the workings of our planet, but also a greater appreciation for the delicate balance that makes life on Earth possible. Earth, our home planet, showcases a harmonious balance in its orbital and rotational characteristics, fundamental to sustaining life as we know it. As we delve into these aspects, we uncover the mechanics that make Earth uniquely hospitable among the planets in our solar system. Earth's orbit around the Sun is nearly circular, with a slight elliptical shape that causes minimal variation in Earth's distance from the Sun throughout the year. This orbit is completed in about 365.25 days, defining the length of one Earth year. This quarter-day surplus is the reason we add an extra day every 4 years, creating a leap year to keep our calendar in alignment with Earth's position in its orbit. The tilt of Earth's axis relative to its orbital plane, about 23.5 degrees, is responsible for the seasonal changes we experience. As Earth orbits the Sun, this axial tilt causes different parts of Earth to receive varying amounts of sunlight at different times of the year, leading to the progression of seasons. Earth rotates on its axis once approximately every 24 hours, defining the length of one day. This rotation is responsible for the day-night cycle, as different parts of Earth's surface are illuminated by the Sun at different times. Earth's rotation direction is prograde, meaning it spins in the same direction it orbits the Sun from west to east. This is why the Sun appears to rise in the east and set in the west in our sky. The speed of Earth's rotation affects the planet in several ways, including the generation of the Coriolis effect, which influences weather patterns and ocean currents. This effect causes moving air and water to turn to the right in the northern hemisphere and to the left in the southern hemisphere, playing a crucial role in the formation of weather systems. The balance of Earth's orbit and rotation is vital for maintaining the planet's climate and conditions suitable for life. The relatively stable temperatures, predictable seasons, and the day-night cycle are all outcomes of these fundamental characteristics. They regulate the environment, helping to sustain the diverse ecosystems found across the globe. Understanding Earth's orbit and rotation not only provides insights into the conditions necessary for life, but also serves as a benchmark for comparing other planets in our solar system and beyond. As we explore the universe, Earth's harmonious orbital and rotational dynamics remind us of the delicate balance that fosters life on our unique planet. Our home planet, Earth, continues to be an endless source of discovery, revealing secrets about its climate, geology, and the intricate systems that support life. Recent advancements in technology and science have led to groundbreaking discoveries that deepen our understanding of Earth and its place in the universe. One of the most pressing discoveries has been the detailed observation and understanding of climate change and its impact on Earth's ecosystems and weather patterns. Satellite data has provided unprecedented insight into rising global temperatures, melting ice caps, and the increasing frequency of extreme weather events. These observations are critical for developing strategies to mitigate climate change and adapt to its impacts. In the realm of geology, scientists have made significant advances in understanding Earth's interior and the dynamics of plate tectonics. Deep-sea exploration and seismic monitoring have unveiled new features beneath the ocean floor, including previously unknown underwater volcanoes and hydrothermal vents, enriching our understanding of Earth's geothermal activity and its role in supporting deep-sea ecosystems. The discovery of microplastics in the remotest parts of the world, from the depths of the oceans to the peaks of mountains, has highlighted the pervasive impact of human activity on the planet. This has spurred a global conversation on sustainability and the urgent need for changes in how we produce and consume resources. Looking to the future, a host of missions and projects are poised to take our understanding of Earth to new heights. The European Space Agency's Earth Explorer missions, such as the Biomass satellite, aim to map and monitor Earth's forests in 3D, providing crucial data for biodiversity and climate studies. NASA's SWOT, Surface Water and Ocean Topography, mission will offer unprecedented detail on the distribution and flow of water on Earth's surface, aiding in water management and environmental preservation. In addition, initiatives like the Argo program, which deploys thousands of floating sensors across the world's oceans, continue to provide invaluable data on ocean temperatures, salinity, and currents. This information is essential for understanding ocean circulation patterns, climate change, and marine biodiversity. The integration of artificial intelligence and big data analytics with Earth observation technologies is opening new frontiers in environmental monitoring, disaster response, and resource management. These tools allow for real-time analysis of environmental data, enhancing our ability to predict natural disasters, track changes in land use and vegetation cover, and monitor the health of the planet. As we continue to explore and understand our own planet, Earth's mysteries unfold, reminding us of the complexity and interconnectedness of the natural world. These discoveries not only enrich our knowledge, but also underscore the importance of preserving our unique home in the cosmos. The future of Earth observation and exploration promises to bring even more insights, inspiring action towards a sustainable future for all inhabitants of our planet. As we conclude our exploration of Earth, our own magnificent home in the vast cosmos, we're reminded of its uniqueness and fragility within the solar system. Earth, with its diverse climates, abundant life, and dynamic systems, stands as a testament to the beauty and complexity of the universe. This exploration of our planet has not only showcased the variety of landscapes and ecosystems, but also highlighted the delicate balance that makes life possible. The study of Earth goes beyond understanding its current state. It's a journey through time that uncovers the past and anticipates the future. It challenges us to think about our role in preserving this balance, ensuring that the planet remains a nurturing home for generations to come. As we learn more about our world, from the depths of the oceans to the upper reaches of the atmosphere, we gain insights into how to better protect and sustain it. The exploration of Earth is an ongoing adventure. With each new discovery, whether it be in the deepest ocean trenches or the highest mountain peaks, we uncover more about our planet's history, its intricate systems, and the life it supports. These endeavors not only enrich our understanding, but also strengthen our commitment to Earth's stewardship. We invite you to stay curious, to cherish the natural world around you, and to consider your part in its preservation. Earth, with its boundless beauty and resilience, is a constant reminder of the interconnectedness of all things. As we continue to explore and understand, let us also act with care and responsibility, ensuring that this planet remains a vibrant and life-sustaining home for all. Thank you for joining us on this exploration of Earth. The journey of discovery is far from over, and we look forward to sharing more about the wonders of our planet and the ways we can all contribute to its future. Welcome to a captivating journey to Mars, the fourth planet from the Sun, often heralded as the Red Planet due to its striking rust-colored surface. This celestial body has been a beacon of fascination and intrigue for astronomers, scientists, and dreamers alike, inspiring countless missions, stories, and even the possibility of future colonization. Mars is not just a neighbor in our solar system, but a key to understanding potential life beyond Earth, the history of our solar system, and the future of human exploration. As we embark on this exploration of Mars, we invite you to discover the mysteries, landscapes, and secrets that this extraordinary planet holds, from its towering volcanoes and vast canyons to the search for water and signs of ancient life. Mars presents a world of wonder waiting to be uncovered. Join us as we delve into the atmosphere, geology, and exploration of Mars, revealing why this planet captures our imagination like no other. Mars is enveloped by a thin atmosphere, a stark contrast to the dense atmospheric shroud of Earth. This Martian veil is composed primarily of carbon dioxide, accounting for about 95% of its atmosphere, with minor constituents including nitrogen, argon, and traces of oxygen and water vapor. This composition is a key player in Mars's climate, a cold desert world where the thin atmosphere contributes to significant temperature extremes and a surface pressure less than 1% of Earth's at sea level. The climate of Mars is characterized by its wide temperature fluctuations, which can be extreme. During summer days at the equator, temperatures can warm up to a relatively comfortable 20 degrees, 68 degrees, inviting comparisons to a cool Earth day. However, the lack of a thick atmosphere means heat dissipates quickly, and temperatures can plummet to as low as minus 125 degrees or 95 degrees near the poles during winter nights. Mars also experiences dust storms, which can vary from small tornadoes of dust called dust devils to planet-encircling events that can obscure the surface from view for weeks or even months. These storms are driven by wind patterns that are influenced by the planet's topography, including its large volcanoes and impact basins. Despite the harsh and volatile climate, Mars shares some similarities with Earth. Its axial tilt is similar to our own planet's, which means Mars experiences seasons: spring, summer, autumn, and winter. However, due to Mars' longer orbit around the Sun, a year on Mars lasts approximately 687 Earth days, making each Martian season last about twice as long as its Earth counterpart. The exploration of Mars' atmosphere and climate is not just an academic pursuit. Understanding these elements is crucial for the future of human exploration and potential colonization. Knowledge of Martian weather patterns, temperature extremes, and atmospheric composition will inform the design of habitats and suits for astronauts, as well as the planning of missions to ensure the safety and success of human endeavors on the Red Planet. In summary, Mars presents an environment that is both intriguing and challenging. Its thin atmosphere and dynamic climate offer a unique laboratory for studying planetary processes, and as we continue to explore and unravel the mysteries of the Red Planet, we gain valuable insights into the workings of our own world and the broader solar system. The surface of Mars presents a landscape both alien and somewhat familiar to those of us on Earth. As we traverse the Martian terrain, we are met with vast deserts, towering volcanoes, and deep canyons that tell the story of the planet's dynamic history. At the forefront of Martian geology stands Olympus Mons, the largest volcano in the solar system. This colossal shield volcano measures about 600 kilometers in diameter and rises 22 kilometers above the surrounding plains, its size dwarfing that of Mount Everest. Olympus Mons is a testament to the volcanic activity that once shaped much of the Martian surface. Adjacent to the volcanic regions, the Valle Marineris Canyon system stretches over 4,000 kilometers across the Martian equator, delving as much as 7 kilometers deep into the planet's crust. This vast chasm, visible even from space, reveals the complex tectonic forces at work on Mars, offering clues about the planet's past geological activity. The Martian surface is also scarred by impact craters, ranging from small, fresh pits to large, ancient basins. These craters are a record of the bombardments Mars has endured over billions of years, providing valuable information about the planet's history and the solar system's early days. But perhaps the most compelling evidence of Mars's dynamic past are the ancient river valleys and delta formations that crisscross its surface. These features suggest that water, the essential ingredient for life as we know it, once flowed abundantly across Mars. Today, these dried riverbeds and deltas stand as stark reminders of a time when Mars may have been home to oceans, lakes, and rivers, painting a picture of a world that might have once harbored life. As we look closer at the Martian soil, we find that it is rich in iron oxide, giving the planet its characteristic red hue. This rust-colored dust covers much of the surface, swirling in the thin atmosphere to create dust storms that can envelop the entire planet. The geology of Mars is a mosaic of features, each contributing to the story of a planet that has undergone monumental changes over billions of years. From towering volcanoes and deep canyons to ancient riverbeds and expansive plains, Mars offers a unique landscape that continues to intrigue and inspire. As we explore this alien terrain, we are constantly reminded of the forces of nature that sculpt planets, including our own, and the mysteries that await us beneath the surface. One of the most captivating questions about Mars has been its relationship with water. Unlike the arid landscape we observe today, evidence suggests that Mars once hosted liquid water on its surface. This revelation comes from the network of ancient river valleys and delta formations etched into the Martian crust, telling a story of a time when water freely flowed across the planet's surface. Today, water on Mars exists primarily in the form of ice. The polar ice caps, visible even from Earth with a good telescope, are a mixture of water ice and frozen carbon dioxide, or dry ice. These caps grow and recede with the changing Martian seasons, offering a dynamic glimpse into the climatic cycles of Mars. Recent missions have uncovered tantalizing evidence of water ice beneath the Martian surface in other regions too. Radar data and lander observations suggest vast reserves of underground ice hidden just below the surface at mid to high latitudes. This ice could be a critical resource for future human explorers, potentially serving as a source of drinking water, breathable air, and even fuel. The presence of water ice also renews hope in the search for past life on Mars. Where water exists, life as we know it can potentially thrive. The discovery of water ice raises questions about the planet's habitability in its ancient past, and whether microbial life could have existed on Mars when it was warmer and wetter. In summary, water on Mars represents both a historical record of the planet's climate and a vital resource for the future exploration and potential colonization of the red planet. As we continue to explore Mars, the story of water will undoubtedly play a central role in unlocking the mysteries of our neighboring world. Mars, often referred to as the red planet, follows an elliptical orbit around the Sun, a journey it completes in about 687 Earth days, defining a Martian year. This extended year means that each of the 4 seasons on Mars, spring, summer, autumn, and winter, lasts nearly twice as long as its Earth counterparts, providing a unique rhythm to the Martian climate and landscape. The rotation of Mars on its axis closely mirrors that of Earth's, with a Martian day, or sol, lasting just over 24 hours, 39 minutes, and 35 seconds to be precise. This similarity in day length has intrigued scientists and space enthusiasts alike, offering a familiar parameter in the otherwise alien conditions faced by missions to Mars. But it's the axial tilt of Mars, at about 2519 degrees, which is responsible for the planet experiencing seasons much like Earth does. However, due to Mars' elliptical orbit, the seasons are not of equal length. Martian summers in the southern hemisphere are warmer but shorter than those in the northern hemisphere, a result of the planet being closer to the sun during the southern summer. Conversely, winters are colder and longer in the south, adding a layer of complexity to the Martian climate. These seasonal changes impact various aspects of Mars's environment, from the extent of its polar ice caps, comprised of both water and carbon dioxide ice, to the frequency and intensity of dust storms, which can engulf the entire planet. Understanding these patterns is crucial for future missions, especially those aimed at human exploration and potential settlement, as they dictate not only the potential for water extraction, but also the challenges posed by Martian weather. As we continue to study Mars, the intricacies of its orbit, rotation, and seasons offer vital clues to its past, present, and future, shedding light on the planet's climate dynamics and its capacity to support life, whether it be microbial life in the past or human life in the future. The journey to understand Mars has captivated humanity for centuries, evolving from ancient astronomers observing its red glow in the night sky to sophisticated spacecraft exploring its surface today. The exploration of Mars has been marked by significant milestones, each bringing us closer to unraveling the mysteries of the Red Planet. Our venture into Martian exploration began with telescopic observations, leading to the mapping of its surface and the early detection of features like the polar ice caps. These observations laid the groundwork for our understanding of Mars, sparking curiosity and a multitude of questions about its environment and potential for life. The modern era of exploration took flight in the 1960s with the Mariner missions, which provided the first close-up images of Mars, revealing a world with craters, mountains, and valleys. These missions were the precursors to a series of orbiters, landers, and rovers designed to study Mars's atmosphere, surface, and potential for habitability. The Viking missions in the 1970s were the first to land on Mars, conducting experiments that searched for signs of life and studying the Martian soil and atmosphere. Although no definitive signs of life were found, these missions significantly advanced our knowledge of Mars and fueled further exploration. In the past 2 decades, rovers such as Spirit, Opportunity, Curiosity, and most recently Perseverance have roamed the Martian surface. These rovers have been equipped with advanced scientific instruments to conduct more detailed analyses of the planet's geology, climate, and potential for ancient life. They've discovered evidence of past water flows, organic molecules, and complex chemical environments that could have supported microbial life. The InSight lander, deployed to study Mars's interior, has provided valuable data on Marsquakes, revealing insights into the planet's internal structure. Meanwhile, orbiters like the Mars Reconnaissance Orbiter continue to map the planet's surface in high resolution, identifying landing sites for future missions and monitoring Martian weather. The exploration of Mars is not just a pursuit of knowledge, but a global endeavor that unites countries and scientists in the shared goal of advancing human understanding of our place in the cosmos. With each mission, we peel back another layer of Mars mysteries, bringing into focus the possibility of past life and the potential for future human exploration. As we look to the future, missions planned by NASA, ESA, European Space Agency, and other international partners aim to return samples from Mars to Earth, explore its moons, Phobos and Deimos, and eventually send astronauts to walk on its surface. The exploration of Mars stands as a testament to human curiosity and our unyielding drive to explore the unknown. Mars is accompanied in its journey around the Sun by 2 small moons, Phobos and Deimos, each with its own unique story. Phobos, the larger of the 2, is a cratered, irregular-shaped body that orbits Mars closer than any other moon in the solar system, orbits its planet. It is gradually spiraling inward, and scientists predict it may either crash into Mars or break apart to form a ring around the planet in the distant future. Deimos, smaller and farther from Mars, shares its siblings' irregular shape and cratered surface, but orbits Mars with much less drama. Its smooth appearance suggests a thick layer of regolith, or space-weathered dust, covering its surface. These moons are believed to be captured asteroids from the nearby asteroid belt, snagged by Mars' gravitational pull long ago. Their composition, heavily cratered surfaces, and irregular shapes support this theory, distinguishing them from the more spherical moons found elsewhere in the solar system. The exploration of Phobos and Deimos has been limited, but they hold significant interest for scientists. Missions to these moons could provide valuable insights into the early solar system, the process of moon formation, and the asteroid belt. Moreover, Phobos in particular is considered a potential staging area for future human missions to Mars, offering a unique platform from which to study Mars and plan surface explorations. As we continue to explore Mars, the significance of Phobos and Deimos in understanding not only Mars, but also the broader solar system becomes increasingly apparent. These moons are more than just celestial companions. They are keys to unlocking the mysteries of the cosmos. As we gaze toward the horizon of space exploration, Mars stands as a beacon for the next giant leap for humanity. The Red Planet is not just a destination for future missions. It represents a new chapter in the human story, one that extends our presence beyond Earth and into the broader cosmos. In the coming years, a fleet of missions is poised to embark on journeys to Mars, driven by an international consortium of space agencies and private companies. These missions aim to further unravel the mysteries of Mars, investigating its atmosphere, soil, climate, and potential for past life. Among them, robotic missions will continue to lay the groundwork for the most ambitious endeavor of all: human exploration. The prospect of human colonization of Mars has transitioned from the realm of science fiction to a tangible goal. Visionaries and scientists alike are drafting the blueprints for human settlement, focusing on the challenges of long-duration space travel, sustainable living in harsh environments, and the utilization of Martian resources for water, air, and construction materials. Initiatives like NASA's Artemis program and SpaceX's Starship aim not just to land humans on Mars but to establish a sustainable presence. However, the journey to Mars is fraught with challenges, both technical and ethical. Questions about the protection of potential Martian life, the psychological and physical effects of living on another planet, and the governance of extraterrestrial colonies are at the forefront of discussions. As we prepare for this next era of exploration, the global community must consider the implications of expanding our footprint into the solar system. Yet the promise of Mars extends beyond the challenges. It offers the potential for scientific breakthroughs, from understanding the viability of life in extreme environments to leveraging Martian geology for insights into Earth's past. Moreover, Mars serves as a proving ground for technologies that could benefit life on Earth, from advanced life support systems to new modes of energy production. As we stand on the cusp of these future missions and colonization plans, Mars invites us to dream big, to confront the unknown with courage and curiosity. It challenges us to envision a future where humanity is not confined to a single planet, but is a multi-planetary species, thriving in the vast expanse of space. In this grand adventure, Mars is not merely a destination, it is a catalyst for growth, innovation, and the enduring human spirit of exploration. The journey ahead will require the best of our collective imagination, ingenuity, and determination. But the rewards, the expansion of human knowledge, the safeguarding of our species, and the unification of humanity in a shared mission, promise to be among the most significant achievements in human history. Thank you for joining us as we look toward the future of Mars exploration. The red planet beckons, and with it, the promise of new discoveries, new challenges, and a new chapter for humanity among the stars. Stay curious, support space exploration, and keep looking up. The next horizon is just within our reach. Welcome to an extraordinary voyage to Jupiter, the colossal guardian of our solar system. Floating majestically in the celestial sea, Jupiter is not just the largest planet in our solar neighborhood, but a world of mysteries, extreme forces, and breathtaking beauty. This gas giant, with its swirling clouds of vibrant colors and storms larger than Earth itself, invites us on a journey to discover the secrets it holds within its immense atmosphere. From the comfort of our own planet, we've long gazed up at Jupiter, a brilliant beacon in the night sky, wondering about the forces at play beneath its dense clouds. Known to humanity since ancient times, Jupiter has been a source of fascination and intrigue, named after the king of the Roman gods for its unmatched size and presence. As we embark on this exploration, we will delve into Jupiter's formation, its vast, turbulent atmosphere, the iconic Great Red Spot, and the mysteries of its powerful magnetic field. We'll journey past its extensive system of moons, each a world unto its own, and glimpse the faint rings that encircle this gas giant. Through the lens of cutting-edge science and the eyes of spacecraft that have ventured far from home, we stand on the brink of unraveling Jupiter's ancient secrets. Join us as we venture into the depths of Jupiter's swirling mists and towering clouds to uncover the dynamics of this massive planet and its profound influence on the solar system. This is the story of Jupiter, the gas giant, a planet of storms and a key to understanding the origins of our cosmic neighborhood. Our journey through the cosmos brings us to Jupiter, a behemoth of gas and mystery, standing as the sentinel of the outer solar system. Born from the same cloud of gas and dust that gave rise to the Sun and the rest of the solar system, Jupiter's formation marks a pivotal chapter in the cosmic story, dating back over 4.5 billion years. In the infancy of the solar system, when the Sun was just beginning to ignite, the remnants of creation swirled in the cold expanse of space. It was within this primordial nursery that Jupiter began to take shape. The planet's immense gravitational pull allowed it to capture and amass a significant portion of the hydrogen and helium that permeated the early solar system, materials left over from the birth of the Sun. This accumulation of gas and dust spiraled together, coalescing into the gas giant we observe today. Jupiter's composition is a testament to its origins, dominated by hydrogen and helium, elements most abundant in the universe, reflecting the composition of the primordial solar nebula. This majestic planet is essentially a miniature star, lacking only the mass required to ignite nuclear fusion in its core. Beneath its swirling clouds and storms lies a sea of hydrogen that, under immense pressure, assumes a metallic form in the planet's depths. This metallic hydrogen generates Jupiter's magnetic field, the strongest of any planet in our solar system, a remnant of the dynamic processes at play in its heart. The lack of a solid surface distinguishes Jupiter from terrestrial planets like Earth. Instead, transitions between phases of gases and liquids define its structure, with atmospheric layers that extend deep into the planet, transitioning into the liquid and metallic hydrogen that make up its bulk. The exact nature of Jupiter's core remains a subject of debate among scientists, with theories suggesting it may be rocky or a dense soup of heavy elements, but its sheer pressure and temperature are beyond the comprehension of our earthbound experience. Jupiter's formation and composition not only highlight its role as the gas giant king of our solar system, but also serve as a window into the processes that shaped the early cosmos. Its existence challenges us to expand our understanding of planetary science, pushing the boundaries of what we know about planet formation, the behavior of exotic materials under extreme conditions, and the diversity of celestial bodies that inhabit our universe. As we delve deeper into the mysteries of Jupiter, we are reminded of the vastness of space and the intricate tapestry of events that have sculpted our cosmic neighborhood. Jupiter, with its bands of swirling clouds and profound storms, stands as a sentinel of our solar system's history, a giant key to unlocking the secrets of the cosmos. Jupiter's atmosphere is a vast, deep layer of gas that envelops the entire planet, extending thousands of kilometers deep. Dominated by hydrogen and helium, the same elements that make up the Sun, this gaseous envelope is home to a complex weather system, unlike any other in our solar system. The atmosphere is characterized by bands of clouds that circle the planet, known as belts and zones, which are created by Jupiter's rapid rotation and the heat rising from its core. These bands vary in color from deep reds and browns to whites and blues, each representing different types of clouds and storm systems. One of the most striking features within Jupiter's atmosphere is the Great Red Spot, a gigantic storm that has raged for at least 400 years, possibly much longer. This colossal storm is so large that 3 Earths could fit within its boundaries. The Great Red Spot's swirling crimson hues are thought to be the result of complex chemical reactions driven by Jupiter's ultraviolet sunlight, acting upon the chemicals in the atmosphere. The storm rotates counterclockwise, with wind speeds reaching up to 430 kilometers per hour, 267 miles per hour. The persistence and size of the Great Red Spot are still subjects of intense study. Scientists believe that the storm has lasted so long due to Jupiter's lack of a solid surface, allowing the Great Red Spot to sustain itself without losing energy, through friction with landforms as storms on Earth do. However, recent observations have noted that the Great Red Spot is shrinking, leading to speculation about its future and what it can teach us about atmospheric dynamics on both Jupiter and other planets. Beyond the Great Red Spot, Jupiter's atmosphere is dotted with numerous other storms and vortices, some rivaling Earth's hurricanes in intensity, but dwarfed by the scale of Jupiter's immense size. These storms offer a window into the dynamic processes that govern Jupiter's atmosphere, driven by internal heat, rapid rotation, and complex chemical interactions. Studying Jupiter's atmosphere and its iconic Great Red Spot not only provides insights into the planet's weather patterns, but also helps scientists understand atmospheric dynamics across the solar system and beyond. As we continue to observe and explore Jupiter with advanced telescopes and spacecraft, we uncover more about this gas giant's secrets, bringing us closer to understanding the workings of the universe itself. Jupiter's magnetic field is a marvel of our solar system, standing as the largest and most powerful planetary magnetic field among all the planets. Generated by the movement of metallic hydrogen deep within Jupiter's core, this magnetic field extends millions of kilometers into space, encompassing Jupiter's many moons and even interacting with the solar wind. This immense magnetic field is responsible for some of the most spectacular phenomena observed in the solar system. At Jupiter's poles, the interaction between the magnetic field and solar particles creates awe-inspiring auroras that outshine those on Earth, illuminating the gas giant's atmosphere with dazzling displays of light. However, the strength of Jupiter's magnetic field is a double-edged sword as it traps a vast amount of charged particles, creating intense belts of radiation that encircle the planet. These radiation belts are far stronger than Earth's Van Allen belts, posing significant challenges for spacecraft. The radiation levels within these belts can damage electronics and pose risks to potential future missions aimed at exploring the planet and its moons. The exploration of Jupiter and its system requires spacecraft to be specially shielded and equipped to withstand these harsh conditions. Missions like NASA's Juno have been designed with these challenges in mind, allowing us to explore Jupiter up close despite the intense irradiation. Juno's orbits are carefully planned to minimize exposure, dipping in and out of the worst of Jupiter's radiation belts, providing invaluable data, while protecting the spacecraft's sensitive instruments. Understanding Jupiter's magnetic field and radiation belts not only helps us in planning future missions, but also offers insights into the workings of magnetic fields around other planets and the potential habitability of moons and planets within such extreme environments. As we continue to explore Jupiter, its magnetic field and radiation will remain key areas of study, unlocking secrets about the planet's interior structure, its atmosphere, and the dynamic space environment that surrounds it. The exploration of Jupiter's magnetic field and radiation belts is a testament to human ingenuity and curiosity, pushing the boundaries of what is possible in space exploration and deepening our understanding of the gas giant's mysteries. When we think of rings around planets, Saturn immediately springs to mind with its spectacular and expansive ring system. However, Jupiter, the gas giant, holds its own lesser-known but equally fascinating ring system. Discovered in 1979 by the Voyager 1 spacecraft, Jupiter's rings were a surprise to scientists, adding a new layer to our understanding of this massive planet. Unlike the bright, icy rings of Saturn, Jupiter's rings are faint and composed mainly of dust particles. These particles are believed to originate from meteoroids crashing into Jupiter's small moons and from material kicked up as interplanetary debris impacts the moon's surfaces. This results in a delicate structure of rings that are difficult to observe from Earth, requiring the close-up scrutiny of spacecraft to reveal their secrets. Jupiter's ring system is primarily made up of three main components: the halo ring, the main ring, and the gossamer rings. The halo ring is a thick inner torus of particles that appears to be about 20,000 kilometers thick and encircles Jupiter at its equator. The main ring, thin but bright, lies next to the halo and is the most substantial part of Jupiter's rings. It's primarily composed of material from the moon Métis and perhaps Adrastea, two small moons that orbit just inside the ring. Beyond the main ring lie the gossamer rings, named for their ghostly, translucent appearance. These are actually two separate rings, one sourced from the moon Amalthea and the other from Thebe. These rings are wider and stretch far out into space, but are much less dense, composed of tiny, dust-sized particles that spread out from their moon sources, creating a gauzy effect. The discovery and study of Jupiter's rings challenge our understanding of ring systems, showing us that such features are not unique to Saturn and that even dust can create an astoundingly beautiful cosmic phenomenon. Jupiter's rings remind us of the dynamic and ever-changing nature of our solar system, with each mission to the gas giant revealing more about its complex nature. As we continue to explore Jupiter and its environs, the rings offer a unique perspective on the interplay between the planet and its moons, the processes that shape their existence, and the dynamic environment of the Jovian system. With future missions and advanced technologies, we hope to uncover more about Jupiter's rings, deepening our knowledge of this majestic planet and its place in the cosmos. Jupiter, the colossal guardian of our solar system, demonstrates some of the most fascinating orbital and rotational dynamics observed in our celestial neighborhood, with a mass more than 2.5 times that of all the other planets combined. Its gravitational influence is immense, shaping the fate of countless objects that venture too close. Jupiter's journey around the Sun is a lengthy voyage, taking nearly 12 Earth years to complete a single orbit. This slow procession through space contrasts with its rapid daily rotation. Situated at an average distance of about 5.2 astronomical units from the Sun, Jupiter's orbit lies beyond the asteroid belt, marking the beginning of the outer solar system. Its path around the Sun is not a perfect circle but an ellipse, with slight variations that have profound effects on the solar system structure, particularly on the orbits of asteroids and other small bodies in the vicinity. The gas giant spins at a breakneck pace on its axis, completing a rotation in just under 10 hours, making it the fastest rotating planet in our solar system. This rapid rotation causes Jupiter to bulge at the equator and flatten at the poles, a phenomenon known as equatorial bulging. This effect is so pronounced that Jupiter has an oblate shape, visibly wider at its equator than from pole to pole. The swift rotation also drives Jupiter's complex atmospheric dynamics, leading to the formation of its iconic banded appearance. These bands are made up of high-speed winds running parallel to the equator, with dark belts and bright zones indicating layers of clouds moving at different speeds and altitudes. The differential rotation, varying speeds at different latitudes, is a direct result of Jupiter's rapid spin, showcasing the immense power of its rotational energy. Furthermore, Jupiter's rotation influences its magnetic field, which is the strongest of any planet in our solar system. The internal dynamo, driven by the rotation of a metallic hydrogen core, generates a magnetic field so powerful it extends millions of kilometers into space, creating a vast magnetosphere that traps charged particles and produces spectacular auroras at the poles. Jupiter's orbit and rotation not only define its own physical characteristics, but also play a crucial role in the solar system's dynamics. Its gravitational might helps to stabilize the orbits of the planets and shapes the paths of comets and asteroids, acting as a cosmic vacuum cleaner that protects the inner solar system from potential impacts. In summary, Jupiter's orbit and rotation are fundamental to its identity as the gas giant king of our solar system. They mold its atmospheric features, drive its magnetic phenomena, and safeguard the planetary order of our cosmic neighborhood. As we continue to explore Jupiter and its intricate system, we unlock further secrets of the solar system's formation, evolution, and the dynamic processes that govern it. The journey to explore Jupiter has been a monumental endeavor, taking us billions of kilometers from Earth to unveil the secrets of the gas giant. This exploration began in the 1970s with the Pioneer 10 and 11 missions, which provided humanity's first close-up images of Jupiter, revealing its complex atmosphere and many moons. Following the Pioneers, the Voyager 1 and 2 spacecraft, launched in 1977, embarked on a grand tour of the outer planets. Their flybys of Jupiter in 1979 offered unprecedented insights into the planet's atmosphere, magnetosphere, and the diverse worlds of its moons. Voyager's discoveries, from volcanic activity on Io to the possibility of a subsurface ocean on Europa, revolutionized our understanding of the Jovian system. The Galileo mission, arriving at Jupiter in 1995, marked the next significant leap in our exploration. Galileo spent 8 years orbiting Jupiter, conducting detailed studies of its atmosphere, magnetic field, and moons. It dropped a probe into Jupiter's atmosphere, sending back data on its composition and dynamics until it was crushed by the immense pressure. Galileo's observations of the Galilean moons further solidified the notion that these bodies could harbor environments suitable for life. In recent years, the Juno spacecraft, which arrived at Jupiter in 2016, has been peering beneath the planet's dense clouds to study its auroras, atmosphere, and structure. Juno's mission is to understand the origin and evolution of Jupiter, looking for clues about the early solar system. Its stunning images of Jupiter's poles and its detailed measurements of the planet's gravitational and magnetic fields are helping scientists solve mysteries about the planet's core, composition, and the vast cyclones that rage at its poles. Looking to the future, the planned Europa Clipper mission, set to launch in the 2020s, aims to closely study Jupiter's moon Europa. The mission will investigate Europa's ice shell and subsurface ocean, assessing its habitability and searching for signs of life. This mission underscores the shift in focus from not just exploring Jupiter itself, but also understanding its moons as potentially habitable worlds. Each mission to Jupiter has peeled back a layer of mystery, revealing a complex, dynamic world that challenges our understanding of the solar system. These endeavors are not just feats of engineering and science, but are a testament to human curiosity and our relentless pursuit to explore the unknown. As we continue to study Jupiter and its moons, we stand on the brink of new discoveries that could redefine our place in the cosmos. The exploration of Jupiter is far from over. It's an ongoing journey that promises to inspire future generations to look to the stars and beyond. Jupiter, the behemoth of our solar system, holds a pivotal role in the celestial dance of planets, moons, and smaller bodies. Its massive size and strong gravitational pull have profound effects that extend far beyond its immediate surroundings. First and foremost, Jupiter acts as a cosmic vacuum cleaner, or guardian of the inner solar system. Its gravitational might helps to steer potentially hazardous comets and asteroids away from Earth. By capturing or ejecting these wandering objects into the outer solar system, Jupiter significantly reduces the number of potential impactors that could cause catastrophic events on our planet, thus playing a critical role in Earth's long-term stability and the safety of life as we know it. Moreover, Jupiter's influence extends to the architecture of the solar system itself. Its gravity has shaped the orbits of planets and the distribution of asteroid belts. The asteroid belt, located between Mars and Jupiter, exists in its current form largely due to Jupiter's gravitational forces, preventing these rocks from coalescing into a planet. This interaction showcases the profound impact Jupiter has on maintaining the balance and structure of our planetary neighborhood. Jupiter's moons, particularly the Galilean moons, present another aspect of its significance. These moons are worlds of their own, with potential subsurface oceans, Europa and Ganymede, that tantalize scientists with the possibility of life beyond Earth. Jupiter's system acts as a miniature solar system, offering invaluable insights into planetary formation, dynamics, and the potential habitability of celestial bodies. In the broader context of solar system formation, Jupiter's early migration is thought to have had a dramatic impact on the arrangement of the early solar system. Theoretical models suggest that Jupiter once migrated inward towards the Sun, before retreating to its current position. This migration could have influenced the formation of the terrestrial planets, including Earth, and the distribution of water in the inner solar system, which is crucial for life. Finally, Jupiter serves as a natural laboratory for studying gas giants and planetary atmospheres. Understanding Jupiter's complex atmospheric dynamics, magnetic field, and internal structure provides clues to the processes that govern other gas giants in our solar system and exoplanets orbiting distant stars. As we conclude our journey through the vast expanse of space to the majestic realm of Jupiter, we're left in awe of the sheer scale and complexity of the largest planet in our solar system. Jupiter, with its swirling storms, powerful magnetic fields, and an entourage of diverse moons, stands as a testament to the wonders that await us in the cosmos. This gas giant is not just a marvel of beauty and power, it's a key to unlocking the mysteries of our solar system's formation and evolution. The study of Jupiter and its moons provides us with clues about the processes that led to the formation of the terrestrial planets, including our own Earth. It challenges us to expand our understanding of planetary systems and to consider the possibilities of life beyond our planet, particularly within the subsurface oceans of its moons like Europa and Ganymed. As we look to the future, Jupiter continues to beckon scientists and explorers with its mysteries. With each mission, from the groundbreaking journeys of Juno to the planned endeavors of the European Space Agency's Jupiter Icy Moons Explorer, JUICE, we peel back another layer of the giant planet's secrets. These missions are not just feats of human ingenuity and curiosity. They are stepping stones towards a deeper understanding of our place in the universe. The exploration of Jupiter also serves as a reminder of the collective ambition of humanity to reach beyond the known, to explore the uncharted, and to continuously push the boundaries of our knowledge. It is a journey that connects us all across continents and generations in a shared quest for discovery. As we move forward, let us carry the spirit of exploration that Jupiter inspires. Let us continue to question, to seek, and to marvel at the universe around us. The story of Jupiter is far from complete, and the greatest discoveries may yet lie ahead, waiting to be uncovered by the curious minds of tomorrow. Thank you for joining us on this extraordinary voyage to Jupiter. May the wonders of the cosmos inspire you to explore, to learn, and to dream of the infinite possibilities that lie beyond our earthly bounds. Thank you for watching. Stay curious, keep exploring, and never stop marveling at the wonders of our universe. Saturn is much more than its rings. As the sixth planet from the Sun, Saturn is a gas giant, primarily composed of hydrogen and helium, sharing this classification with Jupiter, Uranus, and Neptune. It is a world of extremes, with a complex atmosphere, fascinating moons, and a mysterious core that scientists are still striving to understand. In this video, we will delve into the mysteries of Saturn, from its formation billions of years ago to the current exploration missions that seek to unlock the secrets of this giant planet and its numerous moons. We'll explore the composition and structure of its iconic rings, the dynamics of its atmosphere, the intriguing features of its moons, and the role it plays in our solar system. Join us as we embark on this cosmic adventure to discover the beauty, wonder, and mysteries of Saturn. Prepare to be captivated by the sights and secrets of a planet that has been a beacon of curiosity for generations, inspiring awe and wonder in all who look upon it. Stay tuned as we journey through space and time, unveiling the story of Saturn, the gas giant with rings of ice and rock, where each discovery leads us closer to understanding the vast universe we call home. Our journey through the cosmos brings us to Saturn, a planet that embodies the awe-inspiring beauty and complexity of the solar system. Formed over 4.5 billion years ago, Saturn emerged from the same primordial gas and dust cloud that gave birth to the Sun and the rest of the solar system. This gas giant is predominantly made up of hydrogen and helium, elements that were abundant in the early solar system and are key to its classification as a gas giant. The composition of Saturn is fascinatingly similar to that of the Sun, with hydrogen making up the bulk of its mass, followed by helium. This similarity underscores the shared origins of all celestial bodies in our solar system. Yet Saturn's unique characteristics set it apart as a subject of endless curiosity and study. One of the most remarkable aspects of Saturn's composition is its density. Despite being the second largest planet in our solar system, Saturn has an incredibly low density, so low, in fact, that it would float if placid in a vast enough body of water. This peculiarity is due to its gaseous composition, which lacks a solid surface and allows the planet to have a lower overall density compared to terrestrial planets like Earth. Beneath its cloud tops, Saturn hides a core believed to be composed of iron, nickel, and rock, elements that form a solid center amidst the surrounding fluid hydrogen and helium. The pressure and temperature increase dramatically towards the core, creating conditions that are still a mystery to scientists today. The formation of Saturn also played a crucial role in the distribution of materials in the early solar system. the planet's immense gravity attracted and captured a significant amount of the primordial gas and dust, shaping not only its own formation, but also influencing the formation and evolution of its moons and the iconic rings that define its appearance. As we delve deeper into the mysteries of Saturn, its formation and composition continue to provide valuable insights into the processes that shaped our solar system. From its gaseous layers to its solid core, Saturn is a testament to the diversity and wonder of the universe, inviting us to explore further and uncover the secrets it holds. At the heart of Saturn's allure lies its magnificent ring system, an iconic feature that sets it apart from every other planet in our solar system. Stretching out over 280,000 kilometers from the planet, but with a thickness of less than 1 kilometer in most parts, Saturn's rings are a marvel of celestial mechanics and beauty. Composed of countless particles ranging in size from microscopic dust grains to objects as large as mountains, these rings are predominantly made of water ice with traces of rocky material. This composition causes the rings to shimmer in sunlight, creating a spectacle of light that has fascinated astronomers and laypeople alike for centuries. The origins of Saturn's rings have been a subject of debate and research among scientists. One prevailing theory suggests that the rings could be remnants of a moon, or moons that were shattered by high-velocity impacts, or torn apart by Saturn's gravitational pull. Alternatively, they might have formed from the primordial disk of gas and dust that surrounded Saturn during its formation, never coalescing into a moon due to the planet's strong tidal forces. Saturn's rings are not static, but are constantly changing. They are divided into several main sections, named alphabetically in the order of their discovery, from the innermost D ring to the outermost E ring. Each ring has its own characteristics and is composed of smaller ringlets that can contain clumps and gaps driven by the gravitational influences of Saturn's moons and the particles within the rings themselves. The dynamics of the ring system are influenced by a phenomenon known as orbital resonance, particularly with the moons that orbit close to or within the gaps in the rings. These moons, sometimes referred to as shepherd moons, help maintain the structure of the rings, corralling particles and shaping the gaps that add to the complexity and beauty of the system. Recent missions, especially the Cassini spacecraft, have provided unparalleled insights into the rings of Saturn, revealing intricate structures and phenomena such as propeller features, spiraling density waves, and bending waves caused by Saturn's moons and by the planet's own oscillations. These observations suggest that Saturn's rings are much younger than the planet itself and could be as recent as a few 100 million years old, offering a fleeting glimpse in astronomical terms of these stunning natural wonders. The rings of Saturn not only offer a window into the processes that govern our solar system's formation and evolution, but also captivate the imagination with their ethereal beauty. They serve as a reminder of the dynamic and ever-changing nature of the cosmos, inviting us to explore and understand the mysteries that lie within and beyond. Saturn's atmosphere, a vast expanse of hydrogen and helium, presents a captivating yet complex picture of atmospheric dynamics and weather patterns that differ dramatically from those on Earth. This gas giant's upper atmosphere showcases a banded appearance as similar to its neighbor Jupiter, but with bands that are much subtler in contrast due to a thick haze that envelops the planet, diffusing light and obscuring detailed views of the atmospheric storms below. The atmospheric bands are created by high-speed winds in Saturn's upper atmosphere, with speeds reaching up to 1,300 kilometers per hour, about 1,118 miles per hour, some of the fastest wind speeds observed in the solar system. These winds contribute to the dynamic and ever-changing nature of Saturn's atmosphere, sculpting and reshaping the cloud patterns that we see. One of the most striking and enduring features of Saturn's weather is the mysterious hexagonal storm that encircles the planet's north pole. This hexagon, wider than the Earth, has sides each longer than the diameter of our planet and has persisted for decades, if not centuries. Its precise nature remains a subject of research and debate among scientists, with theories suggesting that it's a standing wave pattern in the atmosphere. The hexagon's sharp edges and the rotation of its massive storm system are unlike anything else in our solar system, showcasing the unique meteorological phenomena that can occur on a gas giant. In addition to the hexagonal storm, Saturn experiences massive thunderstorms that can stretch thousands of kilometers across, with lightning bolts far more powerful than those on Earth. These storms can be so intense that they're visible from space, appearing as bright white spots against the planet's creamy yellow hue. The thunderstorms on Saturn are episodic, erupting with fury and then sometimes disappearing for years, adding to the planet's mystique and the dynamic nature of its atmospheric processes. The weather patterns on Saturn are driven by the planet's internal heat, which radiates into space and interacts with the incoming solar energy. This interplay results in complex weather systems that, despite the absence of a solid surface, create a lively and turbulent atmosphere. The study of Saturn's weather patterns not only provides insights into the workings of the planet's atmosphere, but also offers a broader understanding of atmospheric dynamics and weather systems on other gas giants and exoplanets. As we continue to observe and study Saturn, with each discovery, we peel back another layer of its atmospheric mysteries, gaining a deeper appreciation for the intricate and majestic weather patterns that define this gas giant. Saturn, with its stunning rings and enigmatic atmosphere, remains one of the most fascinating subjects in the quest to understand the diverse climates and conditions that exist beyond our Earth. Saturn's magnetic field, while not as strong as Jupiter's, plays a crucial role in shaping the planet's space environment. Generated by the rapid rotation of Saturn's metallic hydrogen core, this magnetic field extends far into space, enveloping the planet in a magnetic bubble known as a magnetosphere. This magnetic shield protects Saturn from the solar wind, a stream of charged particles emanating from the Sun. One of the most captivating phenomena resulting from Saturn's magnetic field are the auroras, similar to the northern and southern lights on Earth. These luminous displays occur when charged particles from the solar wind are funneled along the planet's magnetic field lines towards the poles, where they collide with atoms and molecules in the upper atmosphere, releasing energy in the form of light. Saturn's auroras, however, are not limited to the visual spectrum. They also emit powerful ultraviolet and infrared radiation, making them a fascinating subject for astronomers. Unlike Earth's auroras, which are typically confined to polar regions, Saturn's auroras can cover vast areas and at times even envelop the entire pole. These spectacular light shows are not constant. They vary in intensity and are influenced by the Sun's activity and Saturn's own atmospheric conditions. The interaction between Saturn's magnetic field and the solar wind creates a complex and dynamic system, leading to auroras that are unique to Saturn. The study of Saturn's auroras provides valuable insights into the planet's magnetic field, atmospheric composition, and interaction with the solar system's environment. It also offers a comparative perspective on auroral processes across different planets, including Earth. Saturn's magnetic field and its auroras are not just scientific curiosities. They are emblematic of the dynamic and interconnected nature of our solar system. As we continue to explore Saturn and its surroundings, the mysteries of its magnetic field and the beauty of its auroras remind us of the endless wonders waiting to be discovered in the vast expanse of space. Saturn, the celestial jewel of our solar system, takes an impressive journey around the Sun, completing its orbit approximately every 29.5 Earth years. This grand voyage through space brings with it a unique perspective on time and the changing seasons, unlike anything we experience on our own planet. At the heart of Saturn's day-to-day existence is its rapid rotation. Spinning on its axis once every 10.7 hours, Saturn exhibits one of the fastest rotational speeds in the solar system. This swift rotation significantly influences the planet's appearance, causing it to have an oblate shape. That is, it's noticeably flattened at the poles and bulged at the equator due to centrifugal force. The rapid rotation and extended orbit of Saturn give rise to complex seasonal changes on the gas giant. As Saturn travels its lengthy path around the Sun, each of its hemispheres alternately tilts towards and away from the Sun, resulting in seasons that last over 7 Earth years each. These prolonged seasons affect not just the planet's weather and atmospheric phenomena, but also the visibility and appearance of its iconic rings from our vantage point on Earth. Moreover, the angle at which sunlight strikes Saturn's rings changes as the planet progresses through its orbit, causing dramatic shifts in their appearance. During the equinoxes, Saturn's rings can become nearly invisible to us on Earth, as they are edge-on to the Sun, casting only a thin shadow. Conversely, during the solstices, the rings are tilted towards us, showcasing their full splendor in a breathtaking display of cosmic beauty. These seasonal changes are not merely of interest to astronomers and scientists. They remind us of the dynamic nature of the cosmos, where even the most distant planets undergo transformations and cycles that echo in their own way the familiar seasons we experience on Earth. Yet, the scale and duration of Saturn's seasons serve as a humbling reminder of the vastness of space and the intricacies of planetary systems. As we continue to study Saturn, its orbit, rotation, and the resulting seasonal changes offer valuable insights into the workings of gas giants and the broader mechanics of our solar system. Each observation and discovery peels back another layer of the mystery surrounding this magnificent planet, drawing us ever closer to understanding the complexities of the universe we inhabit. In the grand tapestry of the cosmos, Saturn's orbit and rotation are more than just markers of time. They are a dance of light and shadow, a testament to the ceaseless motion and change that define our universe. As we gaze upon Saturn, we are witnessing the unfolding of cosmic seasons, a spectacle of time and nature on a scale beyond our earthly experiences. The journey to understand Saturn has been one of the most exhilarating chapters in the history of space exploration, marked by groundbreaking missions that have peeled back the layers of mystery surrounding this gas giant. The exploration of Saturn began with flybys by the Pioneer 11 and Voyager missions in the late 1970s and early 1980s, providing humanity with the first close-up images of Saturn, its rings, and moons. Huygens early missions laid the groundwork for what would become one of the most ambitious and successful missions in space exploration history, the Cassini-Huygens mission. Launched in 1997, the Cassini spacecraft carrying the Huygens probe embarked on a nearly 7-year journey to Saturn, arriving in 2004. Cassini's mission was to study Saturn, its rings and its moons, in unprecedented detail. Over the course of its 13-year odyssey in the Saturn system, Cassini made numerous discoveries that have fundamentally changed our understanding of this giant planet, its complex ring system, and its diverse collection of moons. One of Cassini's most huygens achievements was the deployment of the Huygens probe, which descended to the surface of Titan, Saturn's largest moon, in 2005. Huygens transmitted data and images during its descent and after landing, revealing a world with rivers, lakes, and seas of liquid methane and ethane under a thick nitrogen atmosphere. This was the first and, so far, the only landing in the outer solar system, providing invaluable data about conditions on Titan. Cassini also unveiled the dynamic nature of Saturn's rings, discovering new rings and revealing the intricate interactions between the rings and Saturn's moons. The mission provided evidence of active geology on the moon Enceladus, including water-rich plumes ejecting from its south pole, suggesting an underground ocean that could potentially harbor life. The mission's grand finale in 2017, which saw Cassini plunge into Saturn's atmosphere, was designed to protect the planet's moons from contamination, ensuring their pristine environments remain unspoiled for future exploration. This dramatic conclusion to the Cassini mission underscored the importance of responsible exploration and the lengths scientists go to preserve the potential habitability of other worlds. Looking forward, the legacy of Cassini and the earlier missions continues to inspire future explorations. Scientists and engineers around the world are designing new missions to return to Saturn and its moons, eager to build on Cassini's discoveries and to answer the lingering questions about the Saturnian system. These future missions aim to delve deeper into the mysteries of Saturn's atmosphere, the composition and origin of its rings, and the habitability of moons like Enceladus and Titan. As we continue to explore Saturn, each mission brings us closer to understanding not just this magnificent planet, but the workings of our solar system and the potential for life beyond Earth. The exploration of Saturn stands as a beacon of human curiosity, ingenuity, and our unending quest to reach out into the cosmos and uncover its secrets. As we delve deeper into the mysteries of Saturn, it's crucial to understand the unique role this gas giant plays within the tapestry of our solar system. Saturn, with its complex ring system, numerous moons, and immense gravitational influence, serves as a keystone in the cosmic ballet of celestial bodies orbiting our Sun. Firstly, Saturn's gravitational field acts as a shepherd for the solar system, influencing the paths of comets and asteroids. This gravitational pull can redirect potentially hazardous objects away from the inner solar system, including Earth, thus playing a vital role in the safety of our planet. Similarly, Saturn, along with Jupiter, helps to stabilize the orbits of smaller bodies within the asteroid belt, preventing them from clustering into a planet or scattering widely, which could pose a threat to Earth and other planets. The beauty and structure of Saturn's rings also offer a fascinating window into the processes that govern planetary ring systems. These rings, made of ice and rock, provide scientists with a model for understanding the disk of material that once surrounded the Sun, from which the planets formed. Studying Saturn's rings helps astronomers unravel the mysteries of planet formation and the dynamics of celestial mechanics. Moreover, Saturn's moons, particularly Titan and Enceladus, have transformed our understanding of where life might exist beyond Earth. Titan, with its thick atmosphere and liquid hydrocarbon lakes, challenges our concepts of habitability, showing us that life-supporting environments could exist in forms vastly different from those on Earth. Enceladus, with its subsurface ocean and geysers spewing water into space, presents a compelling case for the potential of life in icy worlds. The study of these moons could pave the way for breakthroughs in astrobiology and the search for extraterrestrial life. In addition, Saturn's complex atmospheric dynamics, characterized by powerful storms and the peculiar hexagonal jet stream at its north pole, provide a natural laboratory for studying atmospheric science. These phenomena offer insights into fluid dynamics, weather patterns, and the behavior of gas giants, both within our solar system and around distant stars. In conclusion, Saturn is much more than just a beautiful jewel in our night sky. It is a fundamental component of the solar system that enhances our understanding of planetary science, celestial mechanics, and the potential for life beyond Earth. Its study enriches our knowledge, pushing the boundaries of what we know about the universe and our place within it. As we continue to explore and study this magnificent planet, we can look forward to uncovering more of its secrets, further illuminating the intricate workings of our solar system and beyond. Saturn, with its rings, moons, and mysteries, remains a beacon of exploration, inviting us to question, to learn, and to marvel at the wonders of the cosmos. As we conclude our celestial journey around Saturn, the gas giant that has long captured the imaginations of astronomers and dreamers alike, we are reminded of the vast beauty and complexity of our solar system. Saturn, with its iconic rings and diverse assembly of moons, stands as a beacon of the awe-inspiring wonders that lie beyond our earthly confines. This majestic planet, enveloped in its shimmering bands of ice and rock, not only offers a spectacle of natural beauty, but also serves as a critical laboratory for understanding the processes that govern our solar system. The exploration of Saturn and its moons has propelled our knowledge forward, uncovering secrets about planetary formation, the dynamics of ring systems, and the potential for life in environments vastly different from our own. The legacy of missions like Cassini-Huygens continues to inspire future generations of explorers and scientists. It challenges us to keep looking up, to question what we see, and to pursue the answers with tenacity and wonder. The mysteries of Saturn, from the depths of its atmosphere to the icy geysers of Enceladus and the methane lakes of Titan, beckon us to explore further, to send new missions that will delve deeper into the unknown. As we look ahead, let us carry with us the sense of wonder that Saturn instills. The planet's vastness and beauty remind us of the infinite possibilities that await in the cosmos. It encourages us to dream big, to push the boundaries of our capabilities, and to continue the quest for knowledge that defines our species. The exploration of Saturn is not just a journey through space, it is a journey through the potential of human curiosity and ingenuity. Thank you for joining us on this voyage to Saturn, the jewel of our solar system. May the wonders of the universe continue to inspire you, fueling a lifelong passion for discovery and an unending desire to understand our place among the stars. Thank you for watching. Keep exploring, stay curious, and never stop marveling at the mysteries of our incredible universe. Welcome to a fascinating journey to Uranus, the seventh planet from the Sun, nestled deep within the cold expanse of our solar system. Often overshadowed by its larger neighbors, Uranus holds a unique place in the celestial family as the ice giant, a title reflecting its frigid atmosphere and the icy materials that compose its bulk. With its striking blue-green hue, Uranus stands as a testament to the diversity and wonder of the planets that orbit our star. Discovered in 1781 by William Herschel, Uranus was the first planet found with the aid of a telescope, expanding the known boundaries of our solar system and challenging our understanding of the heavens. Unlike any other planet, Uranus rotates on its side, an oddity that has puzzled astronomers for centuries and has profound implications for its atmospheric conditions, weather patterns, and seasonal changes. As we embark on this exploration of Uranus, we delve into a world of extreme cold, peculiar features, and mysteries waiting to be unraveled. From its unique axial tilt to its faint ring system and intriguing moons, Uranus offers a wealth of scientific insights and curiosities. Join us as we journey to this distant, ice-covered giant, where the outer reaches of our solar system reveal the beauty and complexity of the cosmos. In the vast expanse of our solar system, Uranus stands out not just for its unique features, but also for its historical significance in the realm of astronomy. Discovered on March 13, 1781, by the German-born British astronomer William Herschel, Uranus was the first planet found with the aid of a telescope, a tool that had only begun to transform our view of the night sky a century earlier. Herschel's discovery was monumental, expanding the known boundaries of our solar system for the first time in modern history and challenging the way humans understood their place in the cosmos. Initially, Herschel believed he had discovered a comet, but further observations revealed the truth. This was a new planet, orbiting far beyond Saturn. The discovery of Uranus doubled the size of the known solar system overnight and marked a new era in space exploration, showcasing the power of technology and human curiosity. The naming of Uranus broke from the tradition of using names from Roman mythology. Herschel initially proposed naming the planet Georgium Sidus, George's star, in honor of his patron, King George III of Great Britain. However, this name was not widely accepted outside Britain. The name Uranus, proposed by Johann Elert Bode, was derived from Greek mythology, honoring the ancient Greek god of the sky, Uranos, the father of Cronus, the Roman Saturn, and grandfather of Zeus, the Roman Jupiter. This choice maintained the celestial naming convention and was eventually adopted universally, emphasizing the planet's place among the ancient gods of the pantheon. The discovery of Uranus and the debate over its name highlight not only a pivotal moment in astronomical history, but also the collaborative nature of scientific discovery and the international dialogue that shapes our understanding of the universe. Uranus, with its unique characteristics and distant orbit, serves as a lasting symbol of the boundless curiosity that drives humanity to explore the unknown. In the grand tapestry of our solar system, Uranus occupies a unique and intriguing position. Its journey around the Sun takes approximately 84 Earth years, a stately orbit that places it as the seventh planet from our star. But what truly sets Uranus apart in the celestial dance of our solar system is not just the path it traces through space, but the extraordinary way in which it spins. Unlike any other planet in our solar system, Uranus rotates on its side. With an axial tilt of about 98 degrees, Uranus presents each of its poles to the Sun in turn during its orbit, leading to the most extreme seasons imaginable. This peculiar orientation means that for over 2 decades at a time, large portions of the planet are bathed in continuous sunlight or shrouded in unending darkness. This unique rotation has puzzled astronomers and scientists since its discovery. It's believed that a colossal collision with an Earth-sized object, or perhaps a series of impacts, might have knocked Uranus into this sideways rotation early in its history. The consequences of this tilt are profound, affecting everything from the planet's climate and atmosphere to the way its magnetic field is generated. The seasons on Uranus, as a result, are unlike anything we experience on Earth. Each pole gets around 42 Earth years of continuous sunlight, followed by an equal period of darkness. This has significant implications for the planet's atmosphere, and weather patterns through the full extent of these effects is still not entirely understood due to the limited observations we have made. Uranus's orbit and rotation not only highlight the diversity and dynamism of the planets in our solar system, but also remind us of the violent and chaotic history that has shaped these celestial bodies. As Uranus continues its slow procession around the Sun, it serves as a testament to the complexities and mysteries that pervade our understanding of the universe. In exploring Uranus's orbit and rotation, we are invited to consider the forces at play in the cosmos, the remnants of which are written in the motion and behavior of the planets. Uranus, with its sideways glance at the Sun, challenges our perceptions and compels us to look deeper into the mysteries of the solar system. As we delve into the mysteries of Uranus, one of the most intriguing aspects is its atmosphere and composition, a testament to the planet's status as an ice giant. Unlike the rocky terrestrial planets or the gas giants like Jupiter and Saturn, Uranus presents a unique blend of gases, ices, and possibly an interior ocean, setting it apart in our solar system. The atmosphere of Uranus is predominantly composed of hydrogen and helium, the lightest and most abundant elements in the universe. However, what gives Uranus its distinctive blue-green hue is the presence of methane gas. Methane in the upper atmosphere absorbs red light from the Sun, reflecting back the blue-green light that reaches our eyes, coloring the planet with its signature shade. Beneath this outer layer of methane, the atmosphere of Uranus grows increasingly dense and cold. Temperatures can plunge to as low as 224 degrees Celsius, 371 degrees, making Uranus one of the coldest planets in the solar system, despite not being the farthest from the Sun. This deep chill contributes to the formation of the ices that define an ice giant, water, ammonia, and other hydrocarbons frozen into solid states under high pressure. The composition and structure of Uranus challenge our perceptions of what makes a planet. It stands as a stark reminder of the diversity and complexity of the bodies that orbit our Sun, each with its unique characteristics and mysteries. The study of Uranus's atmosphere and composition not only enriches our knowledge of the ice giants, but also expands our understanding of planetary formation and the potential for life in extreme conditions. As we continue to gaze into the heavens, Uranus serves as a beacon, urging us to explore and understand the vast, cold reaches of our solar system. Its atmosphere and composition are keys to unlocking the secrets of the outer planets and perhaps to answering the perennial question of our place in the universe. In the grand tapestry of our solar system, the rings of Uranus stand out for their subtle beauty and intriguing mysteries. Discovered in 1977, these rings challenged our perceptions, revealing that Saturn was not the only ringed planet. Uranus boasts a complex system of rings, less conspicuous than those of Saturn, but equally fascinating. Composed of dark particles ranging from micrometers to a few meters in size, the rings of Uranus are thought to be relatively young and might have formed from the fragmentation of moons that once orbited the planet. This dark coloration is a stark contrast to the icy brilliance of Saturn's rings, suggesting a different composition or perhaps a covering of cosmic dust. There are 13 known rings encircling Uranus, each named after characters from the works of William Shakespeare and Alexander Pope. The rings vary in brightness and size, with the Epsilon ring being the most prominent. Unlike the broad and reflective rings of Saturn, Uranus's rings are narrow and faint, visible only with the aid of large telescopes or spacecraft flybys. The discovery of Uranus's rings was serendipitous, observed during the planet's occultation of a distant star. As astronomers watched, they noted brief dips in the star's brightness before and after Uranus passed in front, a phenomenon caused by the rings blocking the starlight. This method of discovery highlighted the innovative techniques scientists use to explore the cosmos. The rings' composition and structure raise intriguing questions about their origin and evolution. Scientists speculate that the rings might be relatively recent additions to Uranus, possibly resulting from collisions that shattered one or more of its moons. The exact nature of the ring particles and the mechanisms that confine them to such narrow bands remain subjects of research and debate. The exploration of Uranus's rings offers a unique window into the dynamics of planetary ring systems and their role in the broader context of solar system formation. Understanding these enigmatic structures can provide insights into the processes that govern the birth and death of planetary bodies across the universe. As the only spacecraft to have visited Uranus, Voyager 2's flyby in 1986 provided invaluable data on the rings, but much remains unknown. Future missions to Uranus could further unravel the secrets of its rings, shedding light on the dark particles that compose them and the forces that sculpt their intricate patterns. In the realm of planetary science, the rings of Uranus serve as a reminder of the diversity and complexity of the worlds that share our solar system. They beckon us to look beyond the familiar, to explore the shadows and to discover the stories they hold. As we continue our journey through the cosmos, the rings of Uranus remind us that even the faintest lines can lead to profound discoveries. One of the most intriguing aspects of Uranus is its magnetic field, which defies the norms seen in other planets. Unlike Earth, where the magnetic field is nearly aligned with the rotational axis, Uranus presents a peculiar case. Its magnetic field is tilted at an astonishing angle of approximately 60 degrees from its axis of rotation. Moreover, the center of the magnetic field is not aligned with the center of the planet, but instead it is offset by as much as 1/3 of the planet's radius. This unusual configuration leads to a magnetic field that is dramatically lopsided, creating a complex and irregular magnetosphere. As Uranus orbits the Sun, this tilted magnetosphere tumbles awkwardly, causing rapid fluctuations in the intensity and orientation of the magnetic field around the planet. This unique magnetic setup contributes to the planet's distinct auroral activity, where the auroras on Uranus are not as prominently observed as on planets like Earth and Jupiter. But when detected, they reveal the dynamic and intricate nature of its magnetic environment. The origin of Uranus's peculiar magnetic field remains a subject of scientific fascination and investigation. Researchers propose that this unusual feature may be due to the planet's internal structure, where the magnetic field is possibly generated by motion within Uranus's icy mantle, rather than its core. This theory challenges traditional views on planetary magnetic fields, which are typically thought to arise from the movement of molten metal in a planet's core. Understanding the magnetic field of Uranus is crucial for unlocking the mysteries of not only this ice giant, but also for shedding light on the magnetic phenomena of other celestial bodies, including exoplanets in distant solar systems. The study of Uranus's magnetosphere provides invaluable insights into the diversity of planetary magnetic fields and contributes to our broader understanding of planetary science and the workings of the universe. As we continue to explore and study Uranus, the enigmatic nature of its magnetic field serves as a reminder of the endless surprises our solar system holds. It underscores the need for future missions to Uranus, which could further unravel the complexities of its magnetic field and deepen our knowledge of the ice giants and beyond. The journey to understand Uranus, the seventh planet from our Sun, has been a solitary but significant voyage. The Voyager 2 spacecraft, launched by NASA in 1977, remains the only mission that has flown by Uranus, providing us with a fleeting glimpse into the mysteries of this ice giant. In January 1986, Voyager 2 made its closest approach, revealing details about Uranus that had been hidden from astronomers for centuries. During this historic flyby, Voyager 2 discovered 10 new moons orbiting Uranus, bringing the total known at the time to 15. It also unveiled the complex system of faint rings encircling the planet, a feature that was not well understood prior to the encounter. These rings, composed of dark particles, differ significantly from the bright, icy rings of Saturn, offering a new perspective on ring dynamics around gas giants. Voyager 2's instruments captured the blue-green hue of Uranus, a result of methane in its atmosphere absorbing red light and reflecting the sun's blue light back into space. The spacecraft also measured the temperature of the Uranian atmosphere, confirming it as one of the coldest in our solar system. Perhaps most intriguing were the insights into Uranus's magnetic field, which Voyager 2 found to be tilted at a staggering 59 degrees from the planet's rotation axis and offset from the planet's center. This unusual magnetic configuration leads to complex and dynamic auroras, vastly different from those on Earth. Despite the wealth of data collected by Voyager 2, the visit raised more questions than it answered. The brief encounter provided just a snapshot of Uranus, leaving many aspects of the planet, such as its internal structure, weather patterns, and the composition of its moons, largely unexplored. The need for further exploration is clear. Scientists and astronomers advocate for new missions to Uranus to delve deeper into its mysteries. Proposed missions aim to study the planet's atmosphere, interior, rings, and moons in greater detail, seeking to understand the processes that drive its weather, the nature of its magnetic field, and the geological history of its moons. As we stand on the threshold of new discoveries, Uranus beckons as a frontier of untold secrets. The future of Uranian exploration holds the promise of unraveling the mysteries of this enigmatic ice giant, offering insights not only into the nature of Uranus itself, but into the formation and evolution of the solar system at large. The study of Uranus holds profound scientific significance, offering valuable insights into the formation and evolution of planetary systems. As one of the ice giants, Uranus provides a unique window into the processes that shaped our solar system billions of years ago. Understanding Uranus's extreme axial tilt remains a central mystery in planetary science. Unlike the other planets, which generally rotate upright on their axes, Uranus spins on its side. The cause of this unusual orientation is still debated, with theories ranging from gravitational interactions with other celestial bodies to violent collisions during its formation. Delving into Uranus's interior structure presents another tantalizing puzzle. Scientists suspect that beneath its thick atmosphere and icy mantle lies a rocky core, but the exact composition and properties remain uncertain. Exploring Uranus could provide crucial clues about the formation and differentiation of ice giants, shedding light on their role in shaping the diversity of planetary systems. Furthermore, the potential for an ocean beneath Uranus's icy surface adds another layer of intrigue. If confirmed, this subsurface ocean could harbor exotic forms of life or provide insights into the conditions necessary for habitability beyond Earth. Studying Uranus's magnetic field, auroral activity, and interactions with its moons could offer valuable clues about the presence and dynamics of such an ocean. Despite Voyager 2's groundbreaking flyby in 1986, Uranus remains one of the least explored planets in our solar system. Future missions to Uranus hold the promise of unlocking its secrets, from its enigmatic axial tilt to its interior structure and potential for hosting life. By unraveling the mysteries of Uranus, we deepen our understanding of planetary formation, evolution, and the cosmic forces that shape our universe. As we continue to gaze outward into the cosmos, Uranus stands as a testament to the boundless curiosity and ingenuity of humanity. Its secrets await discovery, inviting us to embark on a journey of exploration and understanding that stretches across the vast reaches of space. As we conclude our journey to the icy depths of Uranus, we are left with a profound sense of wonder and curiosity about this enigmatic planet and its place in the cosmos. Uranus, with its peculiar axial tilt, icy atmosphere, and mysterious rings and moons, challenges our understanding of planetary science and invites us to delve deeper into the mysteries of our solar system. While Uranus may be distant and cold, its significance in our quest to comprehend the formation and evolution of planetary systems cannot be overstated. By studying Uranus, we gain insights into the processes that shaped our own Earth and the other planets in our celestial neighborhood. Its unique characteristics, from its extreme axial tilt to its complex magnetic field, offer valuable clues about the dynamics of planetary bodies and the conditions necessary for life to emerge. Yet, despite the wealth of knowledge gained from the Voyager 2 flyby and subsequent observations, Uranus remains a world largely unexplored, holding countless secrets yet to be uncovered. Its mysteries, from the origin of its rings to the nature of its interior, beckon future generations of explorers and scientists to continue the quest for understanding. As we bid farewell to Uranus, let us carry with us the spirit of curiosity and exploration that drives us to seek out the unknown. Let us continue to push the boundaries of our knowledge, to reach for the stars and to embrace the wonder and awe that the universe offers us. Thank you for joining us on this journey to Uranus, the icy giant at the edge of our solar system. May the mysteries of this distant world inspire us to keep exploring, keep discovering, and keep dreaming of the infinite possibilities that lie beyond our reach. Thank you for watching. Stay curious, keep exploring, and never stop marveling at the wonders of our incredible universe. Welcome to our journey across the cosmos, where today we embark on a voyage to the edges of our solar system to explore Neptune, a planet shrouded in blue mystery and fierce winds. Far from the Sun, Neptune guards the outer realms of our planetary neighborhood, a testament to the vastness and wonder of the universe we inhabit. Join us as we delve into the secrets of this distant world, from its discovery in the night sky to the extraordinary phenomena that ripple across its icy blue atmosphere. Prepare to be captivated by the story of Neptune, the windiest planet, where the dance of gases and ice forms a vision of otherworldly beauty. Let's begin our exploration of this enigmatic giant, a true marvel of our solar system. Neptune, the eighth planet from the Sun, stands as a testament to the wonders of our solar system. Known for its striking blue color, Neptune has been aptly nicknamed the windiest planet because of the astonishingly high wind speeds that sweep across its atmosphere, some of the fastest in the solar system. Unlike its planetary neighbors, Neptune cannot be seen with the naked eye and holds the distinction of being the first planet discovered. Through mathematical predictions rather than direct observation, this discovery underscores the power of human curiosity and ingenuity, revealing a world far beyond our immediate sensory experience. Neptune's blue hue, reminiscent of the ocean, is not just a surface-level beauty, but a clue to its composition. The planet's color is primarily due to the absorption of red light by methane in its atmosphere, allowing the blue light to be reflected back into space, giving Neptune its characteristic appearance. This feature, along with its dynamic weather patterns and fast-moving clouds, makes Neptune a planet of beauty and mystery, inviting us to learn more about the outermost corners of our celestial neighborhood. In the mid-19th century, the planet Neptune was propelled from theoretical mathematics into reality, marking a pivotal moment in astronomical history. Its discovery was not the result of serendipitous observation through a telescope. Instead, it emerged from the calculations and predictions of two brilliant astronomers working independently, Urbain Le Verrier in France and John Couch Adams in Britain. Both men had noticed irregularities in the orbit of Uranus that could not be explained by the gravitational pull of the known planets alone. Through meticulous calculation, they predicted the position of a new, unseen planet. The race to observe this predicted planet was on. The honor of the first sighting went to Johann Galle at the Berlin Observatory on September 23, 1846, just where Le Verrier had predicted it would be. This discovery was a momentous validation of Newton's law of universal gravitation and a testament to the power of predictive mathematics in astronomy. Following its discovery, the task of naming the new planet arose. In keeping with the tradition of naming planets after Roman gods, it was named Neptune, after the Roman god of the sea. This name was fitting, not only because of the planet's deep blue color reminiscent of the ocean, but also as a nod to Neptune's powerful and mysterious nature. Neptune's discovery was a watershed moment in the history of science, highlighting the blend of theoretical physics and observational astronomy, and it expanded our understanding of the solar system's vastness and the laws that govern it. Neptune, our solar system's distant sentinel, embarks on an epic journey around the Sun, one that spans a staggering 164.8 Earth years. This lengthy voyage is a testament to its position as the 8th planet from our star. Nestled in the dark, cold reaches of space, Neptune's orbit, averaging a distance of about 4.5 billion kilometers or 2.8 billion miles from the Sun, showcases the vastness of our solar system and the profound emptiness that lies beyond the inner planets. As Neptune travels on its elliptical path, it showcases a fascinating aspect of planetary motion. Despite its distance, Neptune completes a full rotation on its axis approximately every 16 hours, a day in Neptunian terms. This rapid rotation, juxtaposed with its lengthy orbital period, offers a unique perspective on the diversity of planetary environments in our cosmic neighborhood. The implications of Neptune's orbit extend beyond its sheer scale, influencing the planet's climatic patterns, atmospheric dynamics, and perhaps even the geological and magnetic phenomena that occur deep within. The immense distance from the Sun results in an environment where sunlight is faint, a mere fraction of the warmth and light we enjoy on Earth. This distance plays a crucial role in shaping Neptune's cold, icy exterior and the complex interactions within its atmosphere. Neptune's orbital path also brings it into a delicate gravitational dance with other celestial bodies, particularly its largest moon, Triton, and its interactions with fellow gas giants. These relationships further complicate Neptune's orbital dynamics, introducing subtle variations and resonances that have fascinated astronomers for centuries. In contemplating Neptune's orbit, we are reminded of the scale and complexity of the universe. This distant planet, with its slow, majestic trek around the Sun, embodies the patience and persistence of nature itself, unfolding on a timescale far beyond human experience. As we strive to understand Neptune's place in the cosmic ballet, we gain not only insights into its nature, but also a deeper appreciation for the myriad worlds that orbit our shared star, each with its own stories and secrets waiting to be discovered. Neptune's allure lies not just in its distance from us, but in its very nature, a gas giant shrouded in mystery and extreme conditions. At the heart of Neptune lies a composition that defies the simplicity of categorization. It's a planet that, at first glance, might be thought of as a giant ice ball floating in the dark reaches of space. Yet, this description barely scratches the surface of what Neptune truly represents. Comprising hydrogen, helium, and a smattering of methane, Neptune's composition is similar to that of Uranus, its nearest neighbor, setting them apart as ice giants. The most striking feature of Neptune, however, is its color. A deep, mesmerizing blue engulfs the planet, captivating any onlooker. This is not a simple matter of aesthetics, but a consequence of its atmospheric chemistry. Methane, present in Neptune's upper atmosphere, plays a pivotal role in this phenomenon. It absorbs the red light from the Sun and reflects the blue light back into space, giving Neptune its characteristic hue. This color is not just a feature, but a signature of Neptune's identity in the cosmos. Delving deeper, Neptune's physical characteristics reveal a world of extremities. Its size, with a diameter of about 49,244 kilometers, makes it the fourth largest planet in the solar system. Despite its size and the vast distance from the Sun, Neptune radiates a surprising amount of heat. The planet emits about 2.61 times the energy it receives from the Sun, a phenomenon that challenges our understanding and hints at internal processes not fully understood. Neptune's magnetic field adds another layer of complexity to its character. It is tilted 47 degrees relative to its rotation axis and offset at least 0.55 radii from the planet's physical center. This unusual magnetic alignment suggests a dynamo effect at work, deep within Neptune's interior, where the movement of conductive materials generates its magnetic field. This aspect of Neptune not only intrigues scientists, but also highlights the planet's dynamic internal structure, far from being a passive ball of gas and ice. In essence, Neptune stands as a testament to the diversity and wonder of our solar system. Its physical characteristics, from its composition and color to its heat emission and magnetic field, offer a glimpse into the complexities of planetary science. Neptune challenges us to look beyond the superficial, to delve deeper into the mysteries it holds, and to continue our quest for understanding the universe's myriad wonders. Neptune's atmosphere is one of the most dynamic and intriguing in our solar system, a swirling canvas of blue that hides a tempestuous nature beneath its serene appearance. Composed primarily of hydrogen, helium, and traces of methane, it's the methane that gifts Neptune its captivating azure hue, absorbing red light and allowing the blue to scatter back into space. But beauty in the cosmos often comes with a side of extremity. Neptune holds the title for the most ferocious weather observed on any planet. Winds here howl at unimaginable speeds, reaching over 2,000 kilometers per hour. Nearly supersonic and the fastest by far of any planet. Imagine the fiercest hurricane on Earth, then amplify its power and speed manifold. That's an ordinary day on Neptune. Central to Neptune's atmospheric spectacle is the Great Dark Spot. Observed by Voyager 2 during its historic flyby in 1989, this colossal storm, roughly the size of Earth itself, mirrored Jupiter's Great Red Spot, but with a twist unique to Neptune. Winds at the edge of this dark, anticyclonic storm whirl at breakneck speeds, showcasing the planet's dynamic weather patterns. However, Neptune's storms are not permanent fixtures. The Great Dark Spot had vanished when astronomers looked again with the Hubble Space Telescope a few years later, only for new storms to emerge elsewhere, a testament to the planet's ever-changing weather. Adding to Neptune's atmospheric allure are high-altitude clouds, casting shadows on the blue backdrop below. These clouds form when methane gas freezes, creating ice crystals that reflect sunlight brilliantly, offering a fleeting glimpse into the complex interplay of temperature and pressure in Neptune's atmosphere. Neptune's extreme weather is not just a curiosity, it's a puzzle that challenges our understanding of planetary atmospheres. How does a planet so far from the Sun, receiving only a fraction of its warmth, generate such staggering wind speeds? The answer lies in the planet's internal heat. Unlike Earth, where the Sun largely drives weather, Neptune radiates more than twice as much energy as it receives from the Sun. This internal heat powers the planet's atmospheric movements, driving its winds and storms in a relentless dance of chaos and beauty. As we continue to observe Neptune from afar, each glimpse through the lens of a telescope or the data from a passing spacecraft adds a piece to the puzzle. The study of Neptune's atmosphere and weather not only satiates our curiosity about this distant world, but also enriches our understanding of planetary science and the dynamics of atmospheres far beyond our own. As we delve deeper into Neptune's mysteries, we encounter its fascinating collection of moons and a delicate, almost ethereal ring system that encircles the planet. Neptune has 14 known moons, each with its own unique characteristics and mysteries. However, among these celestial bodies, Triton stands out as the crown jewel. Triton, Neptune's largest moon, is a frozen wonderland that captures the imagination. Unlike any other large moon in the solar system, Triton orbits Neptune in a retrograde direction, suggesting that it was not formed in orbit around Neptune, but was instead captured by the planet's gravity. This intriguing moon is one of the coldest places in the solar system, with surface temperatures plunging to minus 235 degrees Celsius. Despite this frigid environment, Triton showcases geysers, believed to spew nitrogen ice and dust over 8 kilometers into its thin atmosphere, a mesmerizing display of Triton's geologic activity. But Triton is not alone in its dance around Neptune. The other moons, such as Proteus, Nereid, and Larissa, each tell their own story of cosmic ballet, contributing to the complex dynamism of Neptune's gravitational embrace. These moons range in size and composition, offering a diverse array of worlds that hint at the solar system's chaotic past. Circling Neptune, a series of faint rings, add a touch of elegance to this distant planet. Unlike the prominent rings of Saturn, Neptune's rings are thin and sparse, composed of dust particles mixed with ice. These rings are named after astronomers who made significant contributions to Neptune studies: Adams, Leverrier, Lassell, and Gale. The Adams ring is particularly noted for its arcs, unusual clumps of dust and debris that defy expectations by not spreading out evenly, hinting at the complex gravitational interplays at work. Neptune's rings and moons are a testament to the planet's captivating allure, beckoning astronomers to unravel their secrets. Together, they compose a celestial symphony of motion and mystery, playing out in the dark, distant reaches of our solar system. Voyager 2's historic flyby in 1989 marked humanity's first and, to date, only close encounter with Neptune. This monumental event in space exploration provided scientists with a wealth of data, transforming our understanding of the distant planet. As Voyager 2 soared past Neptune, it captured stunning images of the planet's vivid blue atmosphere, intricate ring system, and diverse moons, including the intriguing Triton with its retrograde orbit and active geysers. Despite the passage of time since Voyager 2's visit, Neptune continues to be a subject of intense study and fascination. With advancements in technology, astronomers now use ground-based telescopes equipped with adaptive optics and space telescopes to peer at Neptune from afar. These observations have revealed dynamic changes in its atmosphere, such as the appearance and disappearance of storm systems, and have allowed scientists to study the planet's weather patterns, magnetic field, and complex ring system in greater detail. Looking to the future, there are discussions and proposals within the scientific community about sending a new mission to Neptune. This ambitious endeavor would potentially involve an orbiter and possibly a probe to dive into Neptune's atmosphere. Such a mission would significantly enhance our knowledge of Neptune, helping to answer long-standing questions about its internal structure, atmospheric dynamics, and the mysterious magnetic field. Moreover, Neptune's largest moon, Triton, presents a compelling target for exploration. Scientists believe that Triton, which may have been captured from the Kuiper Belt, could hold clues to understanding the outer solar system's formation and evolution. Investigating its geysers and surface composition could also provide insights into cryovolcanism and the potential for subsurface oceans in icy bodies. As we stand on the brink of new discoveries, Neptune remains a symbol of the vast unknowns of our universe. The continued study of this distant planet not only sheds light on the outer reaches of our solar system, but also fuels our curiosity and drive to explore the uncharted frontiers of space. As we reach the end of our journey through the cold, distant reaches of our solar system, Neptune stands out not just as the furthest planet from the Sun, but as a world of mystery and beauty. From its deep blue hues that captivate our imaginations to the violent supersonic winds that sweep across its atmosphere, Neptune remains a symbol of the uncharted frontiers that lie beyond our current grasp. The discovery and exploration of Neptune, driven by mathematical prediction and the indomitable human spirit of inquiry, underscore our quest for knowledge about the cosmos. Despite the vast distances that separate us from Neptune, our fascination with this icy giant continues to grow. The data gathered by Voyager 2 during its historic flyby in 1989 opened the door to a realm of possibilities, revealing a planet vibrant with dynamic weather systems, intriguing moons, and faint rings that challenge our understanding of planetary formation and evolution. As we conclude, let us reflect on the significance of Neptune in the broader context of space exploration. It reminds us of the vastness of the universe and the endless possibilities that await discovery. Neptune's mysteries beckon scientists and dreamers alike to continue the quest for knowledge, pushing the boundaries of what we know and where we can go. The exploration of Neptune and the outer solar system is not just a journey through space, it's a journey through the depths of our curiosity, and the limitless potential of human ingenuity. Thank you for joining me on this exploration of Neptune. As we continue to gaze up at the night sky, let's remember that the stars above are not just points of light, but gateways to worlds beyond our own, inviting us to discover, learn, and dream. Stay curious, keep exploring, and who knows what wonders we'll uncover next in the vast, beautiful expanse of our universe. Welcome to a journey to the edge of our solar system, where Pluto, once the 9th planet, awaits to unveil its mysteries. Nestled in the vast expanse beyond Neptune, this small world orbits in the cold, dark regions of the Kuiper Belt. For decades, Pluto stood as the final sentinel in our planetary lineup, a mysterious icy orb at the frontier of our celestial neighborhood. Despite its reclassification to a dwarf planet in 2006, Pluto continues to captivate scientists, astronomers, and space enthusiasts alike. Its complex surface, intriguing moons, and unique position offer a window into the early solar system, challenging our perceptions and expanding our understanding of what makes a planet. As we embark on this voyage of discovery, let's explore the history, characteristics, and enduring allure of Pluto. From its controversial discovery to the groundbreaking revelations of the New Horizons mission, we'll delve into the story of this distant world that, despite its size, holds a giant place in our imagination and our quest for knowledge. Join us as we journey to Pluto, a planet in heart if not in classification, and uncover the secrets it has to tell. The quest for a 9th planet began in the late 19th century, spurred by irregularities in the orbits of Neptune and Uranus that suggested the gravitational tug of an unseen body. Astronomers across the globe turned their telescopes towards the heavens, combing the night sky for this mysterious planet. It wasn't until 1930 that the search came to a dramatic conclusion at the Lowell Observatory in Flagstaff, Arizona. There, a young astronomer named Clyde Tombaugh, tasked with the painstaking process of comparing photographic plates of the night sky, discovered a moving object. This object was unlike any star or asteroid. It moved against the backdrop of the cosmos, in a way that could only mean it was far beyond. The discovery electrified the world. The Lowell Observatory, which had initiated the search based on predictions by Percival Lowell, now had the honor of naming the new planet. After much deliberation and countless suggestions from the public, they chose Pluto. The name not only honored the Roman god of the underworld, fitting for a world in the cold, distant reaches of the solar system, but also paid homage to Percival Lowell, with the first 2 letters of Pluto reflecting his initials. Pluto's discovery was a monumental achievement in astronomy, closing the chapter on the search for the solar system's 9th planet and opening a new era of exploration beyond Neptune. The little world, smaller than Earth's moon, captured the imagination of people worldwide, symbolizing the vast, uncharted territories still waiting to be discovered in our cosmic backyard. Pluto, a distant and enigmatic world, lies at the cold outer reaches of our solar system, far beyond the orbit of Neptune. This segment delves into the fascinating characteristics of Pluto, shedding light on its composition, atmosphere, and the dynamic environment that makes it a subject of continuous scientific interest. Pluto's surface is a complex landscape dominated by vast plains, rugged mountains, and deep valleys. Among its most striking features are the towering ice mountains, composed primarily of water ice, which can rise several kilometers above the surrounding terrain. These icy peaks contrast sharply with the smooth, expansive plains such as Sputnik Planitia, a vast ice field made of nitrogen ice, which forms part of Pluto's iconic heart-shaped region. The dwarf planet's atmosphere is thin and tenuous, primarily composed of nitrogen, with traces of methane and carbon monoxide. As Pluto orbits the Sun, its distance varies significantly, leading to dramatic changes in its atmospheric pressure. When closest to the Sun, the ice on Pluto's surface sublimates, thickening the atmosphere and giving rise to a transient blue haze that envelops the planet. This process reverses as Pluto moves away, causing the atmosphere to freeze and fall back to the surface in a never-ending cycle. Pluto's orbit is another aspect that sets it apart from the other planets in our solar system. Highly elliptical, it takes Pluto on a 248-year-long journey around the Sun, during which it can come closer to the Sun than Neptune before moving away to the outermost regions of its orbit. This unique path is inclined at an angle of 17 degrees to the ecliptic plane, further emphasizing Pluto's distinctiveness. Despite its relatively small size, with a diameter of just over 2,177 kilometers, Pluto's gravity has captured 5 moons, with Charon being the largest and closest, so large, in fact, that Pluto and Charon are often considered a binary system. The presence of these moons and the interactions between them add another layer of complexity to Pluto's character. Pluto is not alone in its journey through the outer reaches of our solar system. Orbiting around this distant world are 5 known moons, each with its own unique characteristics and mysteries. The largest and most famous of these moons is Charon, discovered in 1978, nearly half a century after Pluto itself was found. Charon is so large relative to Pluto that they are often referred to as a double dwarf planet system. The gravitational forces between them cause both bodies to orbit a point in space that lies outside either, creating a dance through the cosmos that is rare and fascinating to observe. Beyond Charon, there are 4 smaller moons: Styx, Nix, Kerberos, and Hydra. These moons were discovered more recently, with Nix and Hydra identified in 2005, Kerberos in 2011, and Styx in 2012, thanks to the advancing technology of the Hubble Space Telescope. Their sizes range from just 10 to 50 kilometers in diameter, making them tiny compared to Charon, yet they play a significant role in enriching our understanding of the Pluto system. These moons are thought to be made of water ice, mixed with rock, similar in composition to Pluto, but on a much smaller scale. Their orbits are chaotic and influenced by the gravitational relationship between Pluto and Charon, leading to unpredictable paths that challenge our understanding of celestial mechanics. The existence of these moons provides crucial insights into the history and evolution of the Pluto system. They suggest that Pluto and Charon may have formed from a giant impact, similar to the theory of how the Earth-Moon system came into being. This violent origin might have generated the debris that coalesced into the smaller moons, offering a glimpse into the dynamic and sometimes violent processes that shape our solar system. As we continue to study Pluto and its moons, we uncover more about the complex interplay of forces that govern the outer solar system. These moons, though small, are key players in the story of Pluto, contributing to its character and allure as one of the solar system's most intriguing worlds. The journey of NASA's New Horizons spacecraft, launched on January 19, 2006, marks a monumental chapter in space exploration aimed at uncovering the mysteries of Pluto, the distant icy world at the edge of our solar system. Propelled into the vastness of space atop a rocket, New Horizons embarked on a 9-year voyage, covering over 3 billion miles to reach its primary target. As the spacecraft approached Pluto in July 2015, it began to relay back to Earth the most detailed images and data ever captured of the dwarf planet, transforming our understanding of this distant object. The flyby revealed a stunningly diverse landscape, including towering mountains of water ice, named Norgay Montes and Hillary Montes in honor of the first climbers of Mount Everest. These peaks rise as high as 11,000 feet above Pluto's surface, suggesting geological activity. One of the most captivating discoveries was the vast heart-shaped plain known as Sputnik Planitia, a smooth, bright area made of frozen nitrogen, methane, and carbon monoxide. This region, shaped by the planet's complex and active geology, hinted at a young surface reshaped by internal heat and possibly a subsurface ocean. New Horizons also uncovered signs of an atmosphere. As Pluto moves away from the Sun, its thin atmosphere, composed primarily of nitrogen, with traces of methane and carbon monoxide, freezes and falls as snow back onto the surface. This cycle of evaporation and snowfall creates a dynamic and ever-changing atmosphere. The mission did not just shed light on Pluto, but also provided invaluable data on its moons, particularly Charon, Pluto's largest moon. Charon revealed a varied landscape of canyons, mountains, and plains, along with a unique red cap at its north pole, likely caused by tholins, organic molecules formed by ultraviolet radiation from the Sun hitting methane in Charon's atmosphere. New Horizons' flyby of Pluto was not the end but a gateway to further exploration. After its encounter with Pluto, the spacecraft continued its journey into the Kuiper Belt, a region of the solar system beyond Neptune, filled with icy bodies and dwarf planets, to study other objects that hold clues to the formation of the solar system. The New Horizons mission stands as a testament to human curiosity and ingenuity, pushing the boundaries of what we know about the outer reaches of our solar system and enriching our understanding of the cosmos. Pluto's journey through the cosmic lexicon has been as elliptical as its orbit around the Sun. When discovered in 1930, it was celebrated as the 9th planet in our solar system, a distant and icy counterpart to the rocky and gaseous worlds closer to our star. However, as our understanding of the cosmos expanded, so too did the criteria for what constitutes a planet. In 2006, the International Astronomical Union, IAU, faced a celestial quandary. With the discovery of other large objects in the Kuiper Belt, a region beyond Neptune teeming with icy bodies, the definition of a planet came under scrutiny. To address this, the IAU proposed 3 criteria for planethood. A celestial body must orbit the Sun, be spherical in shape due to its own gravity, and have cleared its orbit of other debris. Pluto meets the first 2 criteria but falls short on the third. Its orbit intersects with that of Neptune, and it resides in the bustling neighborhood of the Kuiper Belt, sharing its space with other icy objects. Based on these criteria, the IAU reclassified Pluto as a dwarf planet, a decision that sparked a debate that continues to this day. Some astronomers argue that the IAU's definition is too narrow and overlooks the geological complexity of worlds like Pluto, which exhibits mountain ranges, vast plains, and signs of past and possibly ongoing geological activity. They suggest that the characteristics of a planet should not solely hinge on its orbital dynamics, but also consider its intrinsic properties. The public reaction to Pluto's reclassification was mixed, with many expressing a sentimental attachment to the planet they had grown up knowing as the 9th member of the solar system family. This emotional connection has fueled ongoing discussions and debates about the nature of planethood and the classification system itself. Despite its demotion, Pluto continues to captivate scientists and laypeople alike. Its classification as a dwarf planet has not diminished its importance in our quest to understand the complexities of our solar system. If anything, the debate over Pluto's status has highlighted the dynamic and ever-evolving nature of science, where definitions are challenged and refined as our knowledge and understanding grow. In the grand scheme of the cosmos, whether Pluto is called a planet or a dwarf planet may seem like a minor distinction. Yet, this debate touches on fundamental questions about how we categorize and understand the universe around us. As we continue to explore the outer reaches of our solar system and beyond, who knows what other celestial bodies will challenge our current definitions and expand our cosmic horizons. Pluto's story is a testament to the unending human quest for knowledge, a reminder that in science, as in space, there is always more to discover. Pluto's journey from its discovery to its reclassification has not only captivated the hearts of astronomers and space enthusiasts, but has also left an indelible mark on popular culture. From being a distant, icy object orbiting the Sun, Pluto has become a symbol of mystery and resilience, sparking imagination and debate across generations. In children's science education, Pluto's story serves as a fascinating introduction to the complexities of our solar system. Textbooks once listed it as the 9th planet, a status that changed in 2006, providing a real-world example of how science is always evolving based on new discoveries. This shift has sparked curiosity and discussions among students about what makes a planet and how we categorize the universe around us. Beyond the realm of education, Pluto has permeated media and literature, often portrayed as the misunderstood or underestimated character that nevertheless holds its own against its larger planetary siblings. Its demotion to dwarf planet status has been the subject of cartoons, jokes, and even protests, highlighting how deeply entrenched it had become in the public consciousness. The debate over Pluto's classification has not only engaged scientists, but has also ignited a broader public discourse on the nature of scientific classification and the emotional connections people form with celestial bodies. For many, Pluto represents the underdog, a small entity in a vast universe that still holds significant importance. This emotional bond has led to a continued interest in missions to Pluto and a keen anticipation of what further secrets it may hold. Pluto's cultural impact extends to its influence on names and terminology. The term Plutoid, for example, now refers to dwarf planets like Pluto that exist beyond Neptune in the Kuiper Belt. This nomenclature keeps Pluto's legacy alive in the scientific community and ensures its continued relevance in discussions about our solar system. As our journey to the distant and enigmatic world of Pluto comes to a close, we're reminded of the boundless curiosity that drives humanity to explore the unknown. Pluto, a tiny speck in the vast expanse of space, has captured the imaginations of scientists, dreamers, and explorers alike. Despite its reclassification to a dwarf planet, its significance in our quest for knowledge remains undiminished. The revelations brought to us by the New Horizons mission have not only expanded our understanding of Pluto, but have also deepened our curiosity about the outer reaches of our solar system and the mysterious Kuiper Belt. Looking ahead, the future promises even more exciting discoveries. Scientists plan further missions to explore Pluto in greater detail, hoping to uncover the secrets it holds deep within its icy heart. Each mission brings us closer to answering fundamental questions about our place in the universe, the formation of planetary systems, and the conditions necessary for life. Pluto's story teaches us an invaluable lesson about the nature of scientific inquiry. It is ever-evolving, driven by both discoveries and debates. The conversation about Pluto's classification has sparked interest and engagement with astronomy like few other topics, reminding us of the passion for exploration that lies at the heart of the human spirit. In the end, whether we call Pluto a planet, a dwarf planet, or by any other name does not diminish its importance. It stands as a testament to human curiosity and our unending quest to explore the cosmos. As we continue to gaze at the stars and beyond, Pluto remains a symbol of the mysteries that await us in the dark corners of our solar system, urging us on in our quest for knowledge and understanding. So as we conclude our voyage to Pluto, let's look forward with excitement to the future discoveries that await us in the vast, uncharted territories of space. The story of Pluto is just one chapter in the grand adventure of exploring our universe, an adventure that promises to captivate and inspire for generations to come. As our cosmic journey comes to a close, we find ourselves back at the crossroads of curiosity and knowledge. We've traversed the vast expanse of our solar system, from the searing heat of Mercury to the icy plains of Pluto, uncovering the secrets of our celestial neighbors. But the universe is vast, and there's so much more to explore. If you've been captivated by the wonders we've shared today, consider this the beginning of an even grander adventure. Your engagement fuels our journey, so if you liked this expedition through the cosmos, please hit the like button. Don't forget to subscribe to Cosmic Crossroads, where the universe beckons and countless mysteries await at every turn. And now, the universe has laid out another path for you to explore. Click on the next recommended video to continue your voyage through the stars. At Cosmic Crossroads, every click opens a gateway to new discoveries, and who knows what wonders lie ahead. Thank you for joining us on this celestial journey. Until next time, keep your eyes on the skies and your spirit ready for adventure. For at Cosmic Crossroads, the universe is always just a click away.